Hello, good morning, good afternoon, good evening, wherever you are. We are really happy to have you all live today from ISU Central Campus in Strasbourg, France, for the MSS TP final presentation of this year's masterclass. My name is Nicolas Peter. I'm one of the faculty of ISU, and I will be with my colleague Daniela, your co-host today. We have the pleasure to have a packed auditorium with us today with the student class of this year in the auditorium. But we welcome also online our esteemed Board of Trustees members, our members of the Academic Council, our ISU Global Faculty, including Dr. Barnaby Osborne, our sponsors from ESA and the Breakthrough Prize Foundation, as well as ISU resident faculty, teaching associates, staff, and of course, ISU students. So ladies and gentlemen, ISU is the sole university dedicated entirely to space education since 1987. So it's really a 35-year success with more than 5,200 alumni shaping the space sector. And today we will listen to the future generation of space leaders, because the Masters of Space Study is the educational hallmark of ISU since 1995. It is a 12-month intensive interdisciplinary graduate program that covered all space domains. The MSS22 class is made up of 35 students from 16 nationalities, and they will present the work done today, but I leave to the floor to Daniela.
Thank you, Nicola. Good afternoon, everybody. Welcome to these who are here in Strasbourg and also to audience online. My name is Daniela Ignjatović-Ogrizović, and it's my great pleasure to welcome you today for presentation on two MSS22 team projects. Team project represents a cumulative work of our MSS master students over the 6 months, having different backgrounds, coming from different countries and cultures. Students during that period are sharing their international, intercultural, and interdisciplinary skills applying into TPs. This year, MSS 22 class was working on two TP projects, TP Starship and TP Direct Energy. Each team had faculty leads in charge to mentoring and guiding their work. For TP Starship, as faculty members, we had professors Nicolas Peter, Gongling San, and Taiwo Tejimola. And for TP Direct Energy, professors Hugh Hill and Bertrand Goldman. Before we start with presentations, I would like to briefly tell you the running order for today's program. From 2 to 3 p.m., first performs TP Starship, following by 30 minutes Q&A session. We'll start with TP Direct Energy at 3:30 p.m. for 1 hour, again following by 30 Q&A session from 4:30 to 5 p.m. Now, I would like to ask you for your attention. For audience via Zoom and our YouTube channel, if you have questions regarding the TPs, please use Zoom chat, but only, I repeat, only during the Q&A session. For the people who doesn't have Zoom access, questions can be addressed via email to faculty leads, to Professor Taiwo Tejimola or Bertrand Goldman. And in the name of the TP Starship project, I'm inviting Professor Tejimola to join us on the stage to moderate TP Starship.
Thank you very much, Nicola and Daniela, for the very kind introduction into what ISU is about and also background about the team project. So it's a pleasure for me to stand here today on behalf of my other two colleagues, Nicola Peter and Gongli Sun, to tell you that we are really very proud, and it's been a pleasure for us to journey with this team on this project. So 19 graduate students have worked on this project in the last 6 months, and they are from 16 countries. So we have no doubt that they have learned a lot academically, teamwork, interculturalness, and all of that. And we are very hopeful, and we believe that this education and what they have learned and the experience they have gained will go with them in their future journey. So we want to say thank you to ESA under the European Center for Space Application and Telecoms, that is actually under the Directorate of Telecoms and Integrated Application. So we have Dr. Bonabe Osborne online, so thank you. So if you have questions, those online, you can just send me via email or use the Zoom chat. I will read it out to the team during Q&A session. Without further ado, I would like to invite the Starship team for their presentation.
Team Project Starship presentation. The Stellar team is delighted to present our interpretation of the impact of Starship on the SatCom industry, told through the eyes of a new space startup company. All characters and events in the following story are fictional. Real-life counterparts are not intended to be represented beyond creative and educational purposes. The year is 2040. Born from the creativity of an interdisciplinary, international and intercultural team, the Stellar company entered the new space scene and propagated a wave of innovation through the satellite communications industry that rippled across the world. The birth of Stellar was catalyzed by the introduction of a revolutionary new launch vehicle from SpaceX, Starship. Starship offered not only an unprecedented cost reduction, but also unparalleled volume and mass capabilities. Starship drove the Starlink megaconstellation to completion and facilitated the launch of an integrated computing system in space, revolutionizing satellite design and end-user applications. Stellar has been a leading player in the space industry this decade, optimizing the sustainability of data resources via direct-to-device techniques, the Internet of Things, and multi-purpose, multi-orbit satellites. The multi-billion-dollar company reduced communication latency and increased the bandwidth to offer a universal internet serving remote and rural areas, aircraft and ships, and supporting in parallel education, healthcare and telemedicine, transportation, and the oil and gas industry beyond all expectations. Our advancements have enabled real-time applications. Telemedicine is our domain. We support millions of people in rural areas by connecting doctors and surgeons with patients thousands of miles away. Healthcare is now within reach of all. The footprint of Stellar extends across the socio-economic, political, legal, technological, and environmental domains. There exists a new global norm, marked by reliable connectivity among humans and machines. Well, let's see together how it all started back in 2022.
Have you seen this rocket? Starship?
Yes.
Yes. Can you imagine if that works? I mean, financially, it might make sense.
Yeah, imagine. I'm not sure if it's even possible.
I have a little faith, Anastasia. You must dream a little bit to be part of the future.
What are you talking about?
The future! We have talked about that. We could start our own company. This rocket could be our opportunity to launch our next-gen satellite. We all know how the future will look like. More connectivity, more data. Come on, Anastasia, I've always known this kind of stuff.
I mean, she could be right. Internet of Things, machine-to-machine communications, in-space telecommunications, worldwide high-speed broadband internet connectivity, maritime in-flight fiber-like connectivity. This stuff is coming, and this rocket could be the key.
Exactly. What do you think, Swapnil?
I mean, like, we might have some problems. If this rocket becomes real, it will disrupt the SatCom industry, and this could give us an amazing opportunity to launch our own business. According to a report, Starship will have the 10 times mass, 4 times volume, 4 times launch cadence, and 10% cost reduction compared to the current launchers available in the market.
Okay, I'm still skeptical, but if it works, we should definitely do it.
I'm telling you, this is the time and this is the rocket. And we will be the company that changed the SatCom industry forever. I know there are a lot of uncertainties and this rocket was not built at the beginning to launch satellites. But we can utilize this amazing rocket to be able, at our advantage actually. And who knows, maybe one day we will end up living on Mars with the billion we will make from our company.
Wait a minute. Billions? Mars? Slow down. What do you even call this company?
Yes, billion. There is a huge market here. As for the name, we will get to that. The prospect for the small satellite market report predict that a constellation will account for 82% of the predicted 7,000 satellites launched by 2027. And a hike in the annual production of small sat is anticipated for 580 in 2022 to 820 per year in the following 5 years. Can you imagine that?
That's great. We will be able to add new technologies and capabilities in our new satellite design, including inter-satellite links that enable multi-orbit constellations. This rocket could deploy more satellites at once or bigger satellites into low Earth orbit. It will be probably launch SpaceX next generation Starlink constellation. It's also possible that the larger, less complex and cheaper GEO satellites could be put into production with bigger antennas, bigger storage capacities, and have even more equipment on board. The possibilities are multiplying.
I totally agree with you. We can do a lot of things if this rocket succeeds. However, I have still some reservation. We can imagine actually some impacts on the current application on Earth and in space. This impact could be on policy, technology, social, and even actually legal domains. And I can already imagine some impact on social and ethical, such as secure connectivity and networking, data privacy, highly skilled job. But I think in our network, we have some people who can help us with that. We know that the new infrastructure allows a business model based on the new radio access networks in LEO and data space centers. Manufacturing high-cadence satellite and being the first one to launch the satellite are the key to being profitable in the first 3 years.
But for that, we will need a big team, a multidisciplinary team.
I totally agree, but I think we know where to find them.
Old classmates.
Exactly.
Okay, and now what about the name?
How about Stella?
Stella was founded by 19 individuals from 16 countries with different backgrounds. Stella will develop state-of-the-art satellite technology to improve daily lives on Earth and address challenges, whilst also heading into deep space to broaden humanity's horizons. Rumours of Starship's development in the early 20s inspired dreams of grandeur in the space landscape. Distant concepts suddenly appeared much closer. The Internet of Things, the integration of everyday items into networks, could be greatly enhanced with space-based systems sharing sensor data, processing information, and controlling devices. Nomadic network applications on moving vehicles could be greatly improved with satellite broadband. Enabling a return to the Moon and a journey to Mars, Starship would generate new notions of connectivity beyond Earth. These dreams, however, would not come without losses. existing companies found it difficult to adapt to the market upheaval Starship generated, opening the door for startups like Stellar to enter the fold. Make no mistake, the space industry would need to adapt quickly. Stellar looked to advise key players on how they can help induce change and consequently help Stellar to flourish under the new paradigm. Before organising a meeting with SpaceX, let's meet our space agency, regulator and industrial partners.
Thank you for joining us today. This meeting between Stellar Company, the SatCom industry, space agency and regulator is really important to us. Why don't you introduce yourself so we know with who we are speaking today?
Sure. Well, hello. My name is Jermaine Gutierrez, and I represent a legal expert at the World Telecommunications Law Group. I do have some questions about the payload volume that I will get to later.
Thank you for inviting me. I speak for the Global Space Agency Consortium. The MSS2 orbit interests me in particular.
Last but not the least, I'm Charles, head of industry and market analysis at SatCom consultancy. I do have some queries about the feasibility of your product, the cost of your operation, and also the market fit. So let's get into it.
Go ahead.
Sure. So as I mentioned earlier, the sheer volume for the constellation that you have planned is sending a couple concerns for us at the WTLG. Allow me to outline three of the major concerns. Those are the radio frequency space allocation, space sustainability, and satellite design drivers. As you're well aware, the ITU allocates radio frequencies based on use cases and across 3 separate geographical regions. You might be happy to hear that your use case for direct-to-device communications and telemedicine applications has been approved as per the registration. But what you may not know is that you now only have 7 years to fully launch your constellation and make it operational. How do you assume to launch such a large constellation in such a tight time frame? The unit numbers of satellites you have given us is quite large. Well, you might be aware such a large number of satellites need to be able to communicate with each other through inter-satellite links. That is to both facilitate efficient data transfer, but also to have a shred of effective situational awareness. Your development of optical inter-satellite links is pushing the ITU to look into creating a 4th region of non-radio frequency space, non-radio frequencies space allocation. Your optical and regular optical inter-satellite checks will be a reality that you should be made aware of.
I appreciate the heads up. You mentioned sustainability?
I did mention sustainability. So the number one reason beyond radio frequency allocation for us is space sustainability. As you know, with every constellation we launch, we put more objects in space, increasing the probability of failure and thus eventually the probability of impact. Space debris generation. What do you think are you doing to mitigate these issues? We see your designs for the satellites involve onboard maneuvering thrusters to be able to get out the way of other incoming satellites. But that's just the basics. What other things are you doing?
Thank you. Actually, indeed, we consider several end-of-life for our satellite design, from desorbiting with our with the atmosphere for our LEO sets to maneuvering and passivation actually into a grave or orbits. And we have a close eyes actually on the space sustainability, given the creation of the space sustainability rating.
I think that is awesome that you hear about the space sustainability rating actually, because that will definitely give you a lot of benefit for your business and will help you to be in front of the sustainability in general, like developing and promoting your social and development governance, you see. It will definitely give you a lot of advantage in terms of debris removal, collision avoidance, but also identification and tracking system. And one of the critical and important point is the end of life that need to be considered by your company.
The final consideration is you should know that the current connectivity market for telecommunications is rather fractured. China does not have an integrated telecommunications law. Both Africa and India have dedicated telecommunications unions, but then again, the Europeans use the European Telecommunications Code. How do you, for your business, assume to adhere to all of these different regulations and laws at the same time? I don't expect an answer right now, but do consider that a large scale of your business may be too large and too complex to be able to handle all of these regulatory differences without being able to address one single authority at the same time.
In fact, national and international space agencies are working closely with our enterprise. And private-public companies allow the access to facility to actually pursue our goal. And I think, Yangon, what roadblocks do you envision?
The high relative mass of your LEO satellite is puzzling. The development of the small sat launcher market is well underway. However, your satellite design, although capable, makes for limited launch solutions available. The space agency facilities in Europe may struggle to meet your projected demand.
Indeed, our LEO satellites are larger than conventional model, but this is a necessary feature due to our optical satellite link and maneuvering tracer for space debris mitigation.
We have also noted your plans for long-range inter-satellite connectivity. Your constellation, if successful, will provide a valuable benchmark for optical inter-satellite links to be able to communicate the data from the ground and to GEO to then be distributed across LEO satellites while minimizing delay is a valuable undertaking.
Yeah, ISU, we have really big plan. Charles, I think you want to add something.
Yeah, of course, you have big plan. That's great. I've run the number and run them again. And there is something I don't understand. The cost to launch is incredibly high. And how can you expect to launch this constellation of this high magnitude without running your business through bankruptcy? The current development of micro launcher deployment are expected to be deployed, in about 30 years with only 2 satellites per launch. So maybe you are going to burn your money through, and for us we call that a valley of death, and in your case it's super wide. We are not saying that everything is bad, actually. It's just that it's already difficult to find funding for a concrete project. Maybe I will be fired, or maybe I will get an office in space. So that sounds good, actually. There is the new space Starship launcher that could be timely and advantageous for your business. I just finished to read the preliminary report, this small preliminary report. Okay, so with this, by reading that, you will see that they plan a massive fairing and extremely high-frequent launches that could be advantageous and help you to reduce your costs and send all of your projected assets on orbit rather quickly. So I believe that the faster you get those satellites on orbit, the better your business will fare.
Thank you so much for this report. So indeed, the increased launch of Starship, cadence of Starship, and actually the elevated satellite deployment are a huge opportunity for Earth. But of course, we must take note and look to resolve the limited factor highlighting during this meeting. So thank you so much for this report. I will read that.
Thank you.
Thank you.
The space players were not wrong. Stellar was taking risks with its futuristic vision. A landscape lacking in regulation meant that updates and changes were likely and could threaten the company's performance. Indeed, the International Telecommunications Union did not regulate the use of optical communication technologies at the time, nor was the space sustainability rating system fully adopted by operators. End-of-life disposal measures were improving, with more and more missions designing their satellite for a natural demise, or inducing a maneuver for controlled atmospheric burnup. But much work still needed to be done to ensure the sustainable use of space. Adopting a larger satellite design, with Starship's increased fairing capacity in mind, meant that launch options would be limited. Stellar's success would depend on Starship. Those involved with the company realised this, and our engineers were far from convinced.
Hey.
Good morning.
Good morning.
It's a pleasure to meet you.
Hi.
Thank you very much for coming all the way here. We're looking forward to hearing what you have to say about Starship's capabilities.
Thank you for welcoming us in your office. So I'm the chief engineer of Starship, and here with me my colleague, engineering specialist Stefania.
Hello. Finally, we are here. I'm Laura and she's Anastasia, and we are Stella engineers. And as you already know through the emails, we are a new satellite startup company looking for the next revolutionary rocket to bring our satellites to space. We want to be able to bring better connectivity around the world. Just think about better telemedicine services. And for that, we are planning to launch our own satellite constellations. Well, our design of our satellites will be futuristic, and we also want with a higher data processing and storage. For that's why we are looking for you, because we are looking for something that can carry increased mass and increased payload volume at frequent launch cadence.
Well, sure. So in this meeting, we will see the overall characteristic of Starship, and we have received your questions prior to this. And this is why we brought some technical drawings. So
okay,
here you can see, we will start with the design of Starship.
So Starship is huge. It's unlike anything you've...
But can you compare it to something we know?
Of course, but let me just start off by saying that in its combined assembly, Starship can stand 120 meters tall, and it has a diameter of 9 meters.
Wait, 120 meters?
Yeah.
Let me see those drawings, because is this a typo?
No, actually this is not a typo. So it's the biggest prospective rocket in the market. And as a comparison, are you familiar with the Saturn V?
Yes, we are.
Well, Starship is bigger than Saturn V, and it had already taken humans to the moon.
That's impressive, wow.
Yeah, and to compare it further with Falcon 9, Falcon 9 had a diameter of 5.2 meters, but Starship has a diameter of 9 meters. So just imagine the possibilities.
That's very, very interesting. Can you give us more details?
Of course. So its total weight when it's on the launch pad is around 4,400 tons.
And actually, to add to this, so to lift such a heavy weight, it uses the super heavy booster. It has lifting thrust of 74 meganewton. It is basically the force that it needs to take it to launch it into the air. So it is twice that of Saturn V, and you can surely use it to have more satellites with the greater mass.
Yes, and to continue, it has a payload volume of 1,100 meters cubed. It's the largest rocket on the market. And furthermore, Falcon 9 could hold around 60 Starlink satellites, but with Starship, you could hold around or more than 300. So you could have bigger and more complex LEO satellites or cheaper and smaller GEO satellites. It really does give you that flexibility.
That is amazing, Anastasia. Just think about what we could do with that. We can launch our satellites in record numbers. So, but I have a question. How about launch cadence? Because we want to launch our satellites every month or maybe more. So what can you tell us?
Yeah. So you have to know that Starship is a fully reusable launch vehicle. So it is easily refurbished, and you can launch it again in a short period of time.
Fully reusable? What about the material? What it's made of?
So it's mostly made of stainless steel, and we chose this as its main material because it's lightweight, it has good thermal conductivity, which means it won't overheat, and it's also pretty cheap and readily available.
Well, I have never seen something like this before. It has increased payload volume and mass for many complex satellites, not to mention an increased launch cadence.
Well, indeed, so the whole team worked really hard, and we will certainly invite you to see the launch.
That's great. But to lift such a heavy rocket, you will need a pretty powerful propulsion system. So what can you tell me about this?
For sure. So Katya had mentioned a few things earlier, so let me just start off by saying that the super heavy part of Starship has around 37 Raptor engines, and it could have a lifting thrust of around 74 meganewtons. And then Starship has 6 Raptor engines, and then it has a lifting thrust of around 12 meganewtons. Do you have any more questions about the propulsion system, or do you want to go into the fairing?
So, I think, how does it work? How can it produce that much thrust?
Of course.
So this is a really good question. So it is, if I have to explain it, it is a full flow staged combustion cycle. It is fueled with liquid methane and liquid oxygen. And this will allow the Raptor to extract the maximum of energy from its propellant.
I'm gonna take all of the notes. Okay, I don't have any more questions about the propulsion, so let's go directly to the fairing and how to integrate satellites with it.
Okay, perfect.
Okay, so as Stefania mentioned, the dimension of Starship is huge, which means that it will allow you to have a great diversity of satellites to be hosted in the fairing. However, the deployment of satellites uses a particular solution. It is something called the clamshell type fairing, which is used to house the payload.
And what exactly is a clamshell type fairing?
For sure. So actually, if you have a look at this visual representation that we have here, so a clamshell fairing, it doesn't open up fully, it doesn't separate, and your payload can be housed in there until it's ready to detach. And we also have special technology, or the right technology, to design special satellite dispensers that can put your satellites into any final orbit that you desire.
That's very, very interesting. But what about compatibility? Can it fit with industry standards?
Yeah, sure. So Starship is compatible with the industry standard. It was the same that we used for Falcon 9. So you don't need to design a separate adapter to use it.
Okay, and so my last question would be, where would you launch from?
Okay, so currently we have two initial launches locations. The first one is the Kennedy Space Center, which is located in Florida. And the second one is in Boca Chica. It is a launch pad in Texas. As per your requirement, you can choose either of the both launch sites.
Okay, that sounds great. This makes it easy for us. I really think that if all of this data works, Starship really can fulfill our requirements.
Exactly. Starship can be a great solution to launch our own satellites. We will talk with our internal team, and we will give you our answer very soon. First, we need to look at the business prospects of this. So thank you very much for this meeting, and I hope that we will work together in the future.
Well, thank you for welcoming us, and we look forward to hear from you.
And you're more than welcome to keep these drawings too.
Thank you very much. We can accompany you to the exit.
The unprecedented scale of Starship was extraordinary by any measure. The fairing diameter was almost double that of the most popular launchers available at the time. Starship could be launched, returned, refueled, reloaded, and launched again, at an incredible pace beyond anything we'd seen before. Constellations could be deployed at an elevated rate, and the number of objects in space could rapidly grow. The integration and deployment of payloads was similar to existing launchers, meaning that operators would not necessarily have to adapt their satellite design to use Starship. The engineering discussions in 2022 yielded positive results, and progress was building towards a viable business model.
Hello everyone, thank you so much for joining me today for our strategy meeting. We really need to get serious about our business model. I know we have some idea how to launch and run our satellite system, but I really think we need something more concrete. Has anyone completing some research?
Sorry. I have completed some, and I think we should launch a constellation of satellites to meet the market's demand.
What do you mean by constellation? Are you talking about astrology again?
Oh, come on, Swapnil, not in front of the boss. No, I'm speaking about hundreds and thousands of satellites in orbit. You can have them at LEO, at above 2,000 kilometers, or also at higher altitude like MEO and GEO. And this is really to meet the demand and the need of customers for fast data processing and high quality service.
But isn't that significantly more expensive than launching the GEO satellite only? Because in the past, it seems like launching a GEO satellite has been the only profitable business model.
Got you, but you know, companies are not used to go under the economy of scale motto. So this means that if you have an efficient production with an increased level of production,
you will have an immense reduction of cost for each project. If we adopt this business strategy for Stellar's constellation project, it would be a huge asset.
I agree, but I have a question. Have you completed any research on the market for the existing satellite communication? Do they have a convincing business model? Because for me, it's kind of questionable.
You have already some launch constellations. You have Starlink from SpaceX, you have Kuiper from Amazon, you have OneWeb, and you have also Ariane Next. So I have here some data to show you a bit what I'm speaking about. So here you go.
Oh, holy, this is intense. These numbers are staggering, actually. They're significantly higher than I expected. It looks like that with their current customer base of 250,000 people, they can replace a constellation of 4,225 satellites every 5 years and still make about 700 million in profit.
Exactly. And if you now focus just on Starlink satellites, you can see that they're expected to deorbit and they have a lifetime of about 5 years. And they have been originally authorized to launch 4,408 satellites, and they recently have the permission to launch 12,000 satellites, and they are expected to be authorized to launch more than 30,000 of satellites. And if SpaceX project succeeds, actually, you maintain this level of growth and have a customer base of 500,000 customers within the next 2 years, it will be enough money to replace a constellation of 12,000 satellites every 5 years. This is really insane.
And I see that Starlink has introduced the premium level of their internet service too, and this will surely increase their revenue even further. I have also heard about another constellation, that is the Iridium Next. I know that they provide Internet of Things services and mobile backhauling, and their revenue figures are quite promising. I know that they have a CAGR of 10% for both customers and revenue, and an approx EBITDA of around 60% for the last 5 years.
That sounds really consistent. I've also done some research into a more niche in modern satellite constellation design. There are two Japanese companies, NTT and SkyPerfect JSAT, that have done a merger to create a joint venture called the Space Compass Corporation for a multi-orbit system where they share data between different levels of altitude for their satellites.
So with the multi-orbit system, you mean that they plan to connect the LEO and GEO satellites?
Yes, exactly, between LEO and GEO. And they want to do even more in the future. So right now, there's a little bit of an issue with low Earth orbit satellites because they are such a low altitude, they have to orbit very fast. And that reduces the amount of time that they can contact ground stations. So in order to fix this problem, they want to route their data from their LEO satellites to their geostationary satellites to increase the amount of time they have to transport their data and also enable the use of optical transmission for high throughput service.
Oh, so I have one question. Do you mean that one GEO satellite will be a route for data from multiple LEO satellites or from observation or data?
Precisely, exactly. So if we want to adopt some of Compass's multi-orbit strategy, we can actually take advantage of Starship. And we can use that to launch both our LEO and GEO segments. And that will reduce our reliance on ground stations and reduce our cost and the amount of money we have to spend on that infrastructure.
Thanks.
But what else does the company wants to do? Because you mentioned that they have other plans for the future.
Yeah, so they want to launch what they call HAPS. These are high-altitude platform systems, usually in the form of drones or blimps. They provide radio services and other things that satellites would do. But they're usually in fixed locations, and they exist usually 20 to 50 kilometers above the ground.
Actually, this is an excellent altitude for observation. And if they have a data direction through a LEO GEO connection, this will just synergize the multi-orbit infrastructure of Compass.
It's a great point.
Yeah, and they also want to use HAPS for a wide area Internet of Things support, for mobile backhauling, to extend mobile networks, and to do logistical tracking of planes, trains, ships, things like this. And they want to fully integrate their HAPS systems with their LEO and GEO systems to create a comprehensive communication infrastructure for all of Japan.
Got you. And I think this could be great to integrate some of this Compass ID into our project because we could have a network of GEO satellites to support the data collection and process of our own satellite, actually.
I fully agree. I think it is important that we incorporate data processing satellite in the GEO to reduce the wasted throughput and processing time for the Earth observation data. By doing post-processing and removing unnecessary data in orbit before it reaches ground can save us immense amount of money, time, and data usage.
I totally agree with you, and I think we really need to review our strategy. We really need to understand how Starship will impact our business model before we proceed.
Actually, I know that
an engineering meeting has been organized with SpaceX, and Anastasia and Laura told me a bit about it, and they told me that Starship will be the first completely reusable rocket, that you have a much higher launch cadence, you have a lower per kilo cost also, and you have an increased total payload mass potential with a much larger payload fairing than what currently exists in the market. And this will allow telecommunication companies like ours to focus on producing multiple satellites for LEO and GEO, and big satellite for GEO actually, like Swapnil said. And this will also be possible to produce multiple satellites with similar features or maybe the same models. And this really rely on this economy of scale motto.
Okay, great of that. But is the Starship business model solid? Because can we afford to base our entire deployment on one rocket?
Yes, from my research, I found out that the Starship business model is solid. NASA's Artemis program is going to use Starship to carry astronauts to the lunar surface, a mission planned for 2024. Another mission which is going to use Starship is removal of space debris from the LEO. Also, Starship can carry hundreds of Starlink at once, and which can accelerate the deployment. This is the key business opportunity for SpaceX, with $885.5 million for the federal subsidies to support rural broadband customers. And I think personally, Starship will be the most preferable launch vehicle in the future.
Well, now that we know that we can rely on it, I think we should discuss Starship's actual engineering capabilities and how we can apply that to our business model.
Absolutely. And based on what we have discussed, let's focus on the four main factors. First, I see we can take advantage of the Starship payload volume. So we can launch almost all our constellation at once actually, and we can also create some redundancy to be able, if there is a problem in space, to have other satellites.
And we can also take one of the main advantages of Starship, that is to increase mass potential to launch larger and more powerful GEO satellites for data processing and multi-orbit systems.
But Damini, don't you think that if we have the larger fairing, then we wouldn't have to go with the complicated satellite designs? We wouldn't need complicated folding solar panels. We can even go with the simpler integration methods.
That's true, but Starship has a main asset. It's called a clamshell fairing, and Anastasia and Laura told me a bit about it. It's a system that adapts to every payload, and if we rely on that, we can reduce research and development costs and also engineering costs. So I think this is a good idea to go with that.
That sounds great. The engineering potential sounds amazing for our satellite design. But also, I think it's important to remember that Starship will have a much higher launch cadence than any of the other rockets that currently exist. And that'll be great for us because if there's sudden changes in demand for our customers, we can immediately respond to that. And we can pick which orbit we need and immediately meet our customers' demand in an effective way.
Starship will also be significantly cheaper per kilogram to orbit. That means it can easily compound with our increasing vertical integration and quick launches. With very small amount of investment, we can expect very high revenue if we launch quicker and with more flexibility with Starship, so that we can achieve the break-even point and achieve profitability even sooner.
Honestly, guys, really great job. I'm really excited to begin presenting the far-reaching impact that our project will have through a multi-causal and multidimensional impact analysis. UNOSA, ITU, and many regulatory agencies are adopting framework that align with Stellar vision. And let's go on that.
Stellar were not the first to envision a complex space network. In 2021, Japanese collaborators unveiled plans for an integrated space computing network. This would include space data centers for handling, storage, and processing in space, reducing the power consumption of systems on Earth, as well as space radio access networks for connecting orbital infrastructure with terrestrial networks. Multi-orbit systems would use geosatellites to extract data from LEO constellations, where fast-moving satellites have very little time to communicate with ground stations. These are good ideas, but would require a vast amount of infrastructure in space to offer an advantage over terrestrial networks. The early stages of the business might struggle to compete, as it would take a long time to launch with traditional launchers. Starship, however, enabled the launch of entire networks and constellations in record time. A higher number of satellites could be launched at an increased pace. Starship was already proving itself in 2022, despite only a few tests having been done. Starship had already won contracts to return astronauts to the surface of the Moon and was integral into accelerating the deployment of the Starlink mega constellation. So Stellar began its flagship project, building an advanced space-based communication network with terrestrial integration. Enabled by Starship, this innovation would change the world as we knew it. The impact of Starship on the SatCom industry enabled developments in other areas, and promised to alleviate some of the challenges faced by humanity in the mid-20s.
So good afternoon and thank you for joining us today. Last time we talked a lot about the complex, company we wanted to do. And I'm really excited and I'm really happy to share that we are launching our launch campaign plans with the Starship rockets. And I think you have to present me some results regarding this bigger impact of this decision.
We have worked with the Leopard of our engineers on the Starship system, as well as closely with the relevant SatCom regulatory authorities and industry consultants. The Leopard specifies the increase in launch frequency, mass, and volume. With 4 times the frequency of launches and 10 times reduced cost compared to current launchers on the market, there are considerable direct impacts. In particular, I'd like to highlight the advantages over frequency and price. When using Starship, we can access space and reduce the metra for high reliability satellites. We can rapidly mass deploy constellations and standardize on cheaper satellite designs. Another advantage is that VLEO can be used for telecommunication satellites to mitigate LEO overcrowding. Jermaine, we have worked closely on this Leopard together, so let us hear your input.
Sure. Charles and I will be standing up to present Marion these results. Thank you, Young-un. You mentioned access to space. Starship, in our eyes, is an enabler. With a planned launch cadence of 3 launches every week and full reusability, the cost of launch is basically dropped down to the price of fuel. Additionally, the manufacturing cost is distributed across the whole lifetime of a single Starship unit. This is more than just a convenience for huge corporations like yours, Madam CEO. This is a barrier reduced for developing nations who will be looking to launch their own satellite constellations in the future. Every nation who was previously unable to to launch satellite systems, not because of a lack of facilities, engineers, or skills, but simply because of the prohibitively expensive launch costs previously observed, is now able to show their might. As such, it is critical that the frequency space remains open and accessible to each sovereign, as it is well in their right. We are absolutely committed at the WTLG to maintain equal access and fair use for each and every country on this planet. And you should be made aware that Stella's contribution to realizing Starship's potential makes this happen. Starship is allowing us to think fairer. The reduced cost barriers means that more competition in developing countries exists between private and public sectors. Stella's decision to use Starship shows that private companies are essentially able to move mountains given the right tools to do so. We at the WTLG are faced with the debate of abolishing the first come, first serve spectrum allocation policy that the ITU observes, because we believe that with reduced cost to launch, newer entrants from developing countries will finally be given the chance to develop their own innovative telecommunication services. Starship is allowing us to think better. Imagine improved connectivity in underserved broadband populations. It is set to promote good health and well-being, increase public safety, and also increase quality education, strongly in line with the UN sustainability goals. This may also lead or start the base of the smart city infrastructure. Virtual classrooms will become essentially commonplace wherever you look, and the privacy laws considering those need to be considered, because we don't want just about any Zoom link to be shared wherever you want. Classrooms will, however, benefit from the removed constraints of physical locations altogether. Other enablements of real-time applications will now be explained by our sector specialist, Charles.
Thank you very much, German. So, Mrs. CEO, before we move to the political, technological, and socio-economic implication, let's have a look to the acceleration of the telecom business model that will directly impact and have a direct link to with the 4 pillars you consider, but also the agency, regulator, and the industry. The integrated space computing network that you are planning to set will lead to a big constellation management issue with high upfront investment challenges. So you should consider the multi-orbit, multi-purpose satellite constellation through its power and volume as shown in this graph that we designed for the purpose of this meeting. From this slide, you can see the increase of the better LEO connectivities through the geo wide angle nodes that we projected. We expect also a better throughput as geo act as data cache. We also consider the backbone of SatCom infrastructure that will offload the data hotspot on the ground. Another important element that certainly you consider already will be the reduced necessity for the ground station that will increase the reliability and reduce the latency. From our perspective, actually we consider that this constellation and the data center will definitely follow the rules of the first to deploy, first to set the standard. So, Mrs. CEO, you should also consider that the increased spectrum interference will be something to consider, like both for space to ground and space to space. As you know already, the traditional space project have stringent the size and mass constraint. So Starship, huge payload and fairing volume will definitely, thanks to also the trust, will increase the capability and capacity to think about like larger technological demonstration and also for communication and beyond. Yeah. So I have a good news kind of. You will not have to fight anymore for kilogram or no more maybe for grams. So, Young-hoon, you were much concerned about like the impact, I think.
Yes. Now, a quick look at the political and social impacts. It makes the commercial space sector grow in both international and national level. International guidance like ITU's frequency and orbit allocation control the growth. Nationally, it can increase the public-private partnership, and it increases the of mega constellation and activates them. In terms of social impact, it increases connectivity with smart cities, airplanes, and boats. First, improves the digital industry and autonomous event gaming industry, and makes healthcare services like telemedicine better. However, some ethical issues linked to Mars settlement, global warming, and space infrastructure. I could also mention the private space company and introduction of new technology with the risk of monopoly.
Awesome. I will continue with some others impact. So glad that the agencies mentioned the connectivity, and previously we mentioned also the public-private partnership. We consider some potential impact in terms of economic and also technology. So the 5G or even the 6G will definitely be more profitable with a lot of opportunities for data business or digital market or industry. You should also consider the increased amount of investment that will be allowed thanks to the new private actors coming in the game. That will definitely allow the free access to space for everyone. That is awesome. We can also, in terms of technology, we expect some, I will say, advanced technology that will kind of mesh thanks to all the services that you are going to offer, especially the virtual reality, augmented reality, but also telemedicine. That is one of the applications I really like that you develop. But also I want to touch into the advanced weather monitoring that will help you to also support the Sustainable Development Goal and tackle the disaster risk management worldwide. However, you should consider some potential impact like related to security. For example, we have the laser blinding, that is a huge topic, the electromagnetic pulse attack, and also electronic attack. So all of that are some of the impact you should consider in terms of technology. Some of them are also related to Starship directly. That will definitely help you to think about like some potential like larger batteries, multiple solar availability that will help you to sustain kind of your business. That's really cool, and definitely you will have to think twice for your design. That will be more easier. Another thing will be the Leo constellation that will be so easy to achieve at the end. We talked about space sustainability rating previously. As industry, we are also concerned about like your social environmental footprint and responsibility, including in outer space. So 3 launches as a week from Boca Chica, for example, is going to cause an unacceptable level of regular extreme noise or vibration or other aspect. We must consider the impact on pollution, definitely, and as one of your supplier, you should maybe take care of that. In addition to others like environmental impact, I want to touch into some of the fact that the environmental impact of on the atmosphere is still unclear. As you certainly know, the FRR final Starship assessment is still incomplete. So that doesn't really matter because you are going to deal with that with them. The increased density of LEO satellite with issue on astronomy and space transportation is also really relevant. I will end with the question of the mineral resources extraction. As you know, Mrs. CEO, some of the rare earth materials remains unexplored, and I'm sure for space infrastructure you will have to be more aware about that and take that into consideration. So it is critical to detect like the correlation between launcher deployment, launch campaign, and mineral extraction. Thank you very much.
Thank you, Charles. So I'll just lay out one last bit, current legal environment that's going on. So first of all, the geostationary orbit allocation is an increasingly hot debate, especially with new entrants coming, and there's no end in sight of where that's going to be. The legal framework for mega constellations is still in complete draft process, and the licensing and environmental approval, as Charles touched on it earlier, needs to ramp up, and it needs to ramp up considerably to match the high launch cadence, not just of Starship, but of all the small launcher developments that are happening right now. To end, Starship is a multi-purpose launch vehicle, built for both human exploration as well as for cargo transportation, for the SatCom industry, for militaries, and for civilian cargo. It is through its high cadence that allows for rapid deployment of standardized satellite systems. And as a consequence, the resilience of these satellite systems increases, whether it's due to outages from geomagnetic storms or even anti-satellite tests. We expect that the development of Starship has a direct geopolitical impact on the geopolitical landscape, because by removing the vulnerability of satellites, because it removes the vulnerability of satellite systems that build up the backbone of the digital infrastructure that we are so dependent on today.
Thank you so much. I'm really impressed by your work and the level of detail. It's completely aligned with what I had in mind. So let's take a break, and after that we have to write our recommendation. Thank you so much.
Thank you, Mrs. CEO. Yeah, I heard that they have like sushis.
It's an incredible story. Starship had been designed to take humans further than ever, not only to land on the moon, but to enable a permanent human presence on Mars, creating opportunity for scientists, explorers, adventurers, engineers, and space architects to go where no humans had gone before. It also encouraged creative thinking to force us to look and to reach further, to identify, to analyze, and to address risks. This led to solutions and spin-offs which helped life on Earth to tackle climate change and space debris and provide telemedical care to those in need. All of these aspects were indirectly enabled by Starship, despite its ultimate purpose, to explore deep space. Now, I'm speaking to you from my office on Mars, but I didn't always work from here. Without Starship, I'd still be speaking to you from our old office in Strasbourg, where we started Stellar. A permanent human presence on Mars was spearheaded by SpaceX and the development of Starship. Now Stellar is looking to develop infrastructure in Martian orbits. Just as we built the integrated space computing network around Earth, we want to replicate that here. Stellar will achieve the ultimate feat of connectivity, connecting Mars to Earth with an interplanetary internet. Stellar would not be as successful as it had been if it were not for some key changes that occurred at the start of the 20s. A team from the International Space University produced a set of recommendations that would allow the space sector to reap the maximal extent of benefits from Starship. At the time it was introduced, the space sector wasn't completely ready to leverage the full capabilities that Starship would offer. Regulation, for instance, was lagging behind the rates of technological advancement. The 3 existing regions over which the ITU operated were no longer sufficient, given the scale and complexity of emerging space networks. Considering space as a new domain was vital in increasing the efficiency of new assignments to orbital slots and promoting the appropriate use of the spectrum. Regulators needed to encourage responsible operations in space and led the way in showing flexibility and adaptability in what was becoming a rapidly dynamic landscape. Building the Space Integrated Computing Network was made possible by fostering relationships between space agencies and SatCom players. These collaborations took advantage of Starship's increased payload mass and volume capabilities, just as the Space Shuttle was imperative in building the International Space Station almost 40 years ago. Satellite design had the potential to be revolutionized by Starship. The addition of more complex, state-of-the-art technologies like optical communication and AI data management systems onto satellites would require more power. To meet these elevated power requirements, more efficient solar panels, or larger or more numbers of solar panels would be needed. Indeed, it was less costly to manufacture more solar panels than to invest in increasing their efficiency only. And in turn, the increased number of solar panels on satellites led to larger satellites. Typically with traditional launchers, the rule was that when the fairing space was available, it was always filled. And this was the case with Starship as well. And this meant that entire constellations of larger, more advanced satellites could be deployed with just a few launches. Now, of course, a densely populated low Earth orbit region of satellites communicating with optical links brought about new regulatory concerns. At the time, optical links were not yet regulated by the ITU, and many operators looked to exploit this gap in the legislation. Eventually, this was added to a World Radio Conference agenda, and appropriate legislature was passed. In addition, compliance with the Space Sustainability Rating System was more important than ever. Space debris threatened to constrain our space activities, but sustainable usage and active debris removal measures greatly reduced this risk. Now, Stellar entered the space scene at the perfect moment to leverage the benefits of Starship and epitomize modern notions of global connectivity and the beginning of humanity's adventure beyond Earth. Ladies and gentlemen, thank you very much for your attention this afternoon. We have been honored to present our interpretation of the impact of Starship on the SatCom industry. I'd like to invite the rest of our team back to the stage before opening the floor to you for any questions you may have. Thank you very much indeed.
Thank you very much for your beautiful presentation. We've learned a lot, and it's been the last 1 hour. You've used it very efficiently. So we are going to move ahead now to Q&A session. You moderate that from this side, okay? So let the answer be brief because we have 30 minutes and we have in the on site, about 6 or 7, and maybe 2 or 3 online. Okay, so I start. From Professor Virginia.
Thank you, Taiwo. So good job, everybody. Very, very interesting concept in your presentation style. But I'll tell you, I'll be honest with you, I had a hard time connecting with it. I do not enjoy going to business meetings. I just learned that I really don't engage while watching other people have business meetings. So I think there were maybe other ways to tell your story that would be a little more engaging. Now I could see that y'all had a really good time doing this, and that's cool. It probably did help you rethink everything that you were learning, and you're nodding, and yeah, so I can see that it was effective for you that way. I think it was a little less effective for engaging an audience though. Regardless, you seem like you know your stuff now, and that is really a great thing to see. I have one question about an apparent paradox. And Tom, you doubled down on this in your closing. Stella, the Starship can help reduce orbital debris. It can be used in this way. And it is really not intuitive. By sending up so many more thousands and thousands of things into space, how are you reducing debris? So that connection is not obvious. So I think maybe that needs a little more explanation.
Yeah, it's a very good point, and it's something that definitely needs to be considered. There have been some sort of speculation and some rumors that Starship could be used as a facilitator for active removal techniques. So it could deploy nets or harpoon systems, for example, in space. However, it's a good point that because Starship will launch more frequently, will launch more at a time, you are injecting a higher number of objects into low Earth and into Earth orbit, not just low Earth orbit. However, it's important to remember that these objects are becoming increasingly more controllable. Every Starlink satellite is fitted with a collision avoidance and onboard propulsion system. When you're launching these satellites with Starship, it's no longer as much of a threat as a passive piece of debris, which is uncontrollable and very difficult to track. So I think in encouraging responsible operations, such as collision avoidance and onboard propulsion systems, you minimize the risk and you allow us to reap the maximal sort of extent that you can by leveraging the increased capacity of Starship to deliver more satellites into orbit.
Very good answer, thank you.
Thank you.
Thank you very much. Thank you, Taiwo. Heartiest congratulations, TP Starship. I thoroughly enjoyed your presentation and didn't look at my watch once. So which is a good indication if you get my meaning. I found it engaging and very clear, most notably the introduction and the conclusion, and appreciated the very good and pedagogic idea of having a storyteller in the form of Tom transitioning from one section to the next. So well done. Also the team coordination and team spirit was very impressive. You can see that you worked really well together, so that's something I really respect. A few questions if I may. Virginia, you stole one of my questions about space debris, but I forgive her on this occasion. The other question is, well, it's very obvious this is a major and very ambitious project. What consideration have you as a team given to new green technologies, such as cleaner propellants?
Thank you for your question. I'm going to give this to Charles to answer.
Thank you very much. So to answer briefly to this question, Starship has a reusable, I would say, technologies that include the use of some propellant that are more clean than the previous propellant used for the thruster and the engine. Another element is the green energy is part of the regulation that we are trying to also push through our recommendation in order to kind of set a standard that will help to promote a green, I would say green space access by using more sustainable way, like technologies. So in short, there are several technologies already developed by Starship or by by SpaceX, sorry, but there are others that need to be considered and regulated properly within the space industry, and that's part of our recommendation.
Yeah, just and a final question. Thank you very much. Final question, if I may. You didn't go into much detail about your interaction with your colleagues, such as ESA colleagues in the UK. Could somebody summarize your interaction with external consultants and benevolent people?
Definitely, Marianne can take that.
So thank you for this question. Actually, we didn't have a lot of interaction with them. So we had in total 3 meetings. Once at the beginning to explain us the project, one in November, December, actually at the end of the literature review, to know if we were in track and if it was good for them, and another one in January, mid-end January, at the beginning actually of the final report, to be sure like we were good in what we wanted to do. And unfortunately after that we didn't have any news. I knew some of our ESA sponsor is online today, so thank you so much for joining, but that's it.
All right, well, thank you very much for a very nice presentation, in quotes. I think you did well. I'm skeptical of the format as well, but I think hearing as well, as Virginia said, that you've learned from preparing the presentation, which is usually the case, but I think it was really true this time, and that's excellent in itself. I would have a couple of questions. So maybe following up with your story of your company, what is your company ready to do to help astronomers accept your contribution to the occupancy of LEO? Are you buying them a telescope in L2, or what do you plan to do?
So thank you very much for the question. And it's a very, very valid concern. As we've seen, Starlink and other mega constellations have been threatening ground-based astronomy and the clarity of observations, both in visible and the radio part of the spectrum. I think what's very special about Starship is that you mentioned taking a telescope to the L2 point, for example, is now far easier with Starship than it ever has been before. Starship has enough thrust to produce enough delta V to inject straight into a geostationary transfer orbit, which then you would use to go to a trajectory beyond GEO to L2. In terms of protecting clear and quiet skies, the International Astronomical Union recently passed or created a working group to work with companies like SpaceX, companies like Amazon Kuiper and OneWeb to maintain and try and protect the clear and quiet skies. So it's harmonizing the relationship between astronomers and the constellation operators. So by encouraging a positive forum, if you like, for productive conversations to occur, I think is key to the root of the problem. I think if you can communicate the problem and the solutions easily, then they will both be made more clear and they will come about a lot more effectively.
All right, very good. My second question would be about maybe defense. So it's clear from the events of 2022 that this kind of technology will be very useful in various situations. And is your company working with governments already? Do you think that governments will have their own constellation of satellites for military purposes only? What is your take?
That's a good question. I'll give this to Charles to take your question.
Thank you very much. In terms of risk management in general, we draw a risk management schedule that includes some of the safety issues related to dual use or maybe military use of certain technologies. It is noticeable that maybe others that could mesh like the topic you are highlighting. However, we have several type of security issues, as we highlighted, like laser blinding, jamming issues that has been highlighted in the report that needs to be considered. And whether it is from the government or not, like private companies, these need to be regulated somehow. And we think that we should set kind of the framework in order to secure any space activities or product in terms of risk management. So thank you.
All right, that's one thing, but I think my question was more about, do you expect one or several governments to be one of your clients, or do you think that they will have their own constellation?
As any private company, for sure we will be open to both private, individual, and government, I would say, services and product. So we will be open, and definitely we will deserve maybe some government under some disclosure kind of. Thank you.
Thanks.
Okay, thank you. And it's really a very nice presentation. And because I'm sitting in the theater, I'm in a VIP position, so I can see it clearly. And I worked in ISU for 5 years. This is the best. I mean, for the performance, the best in my working here. And who is the writer of the script?
So we had several writers in our team. It was Damini's original idea to do a play, and she sort of took over the storyline, and then we had a lot of input from everyone else in the team. Tom, Marion, Swapnil, I can name everyone that had some input into the script and what they wanted to say and bring into the report.
Okay, it's really, really great, and really sure kind of team working together. And my question is mainly for the technical issues, and maybe who can take the microphone, and then I can have several quick questions. Oh, sorry. I'm going to asking some very quick questions. And for the Starship itself, and Elon Musk invented this one is a lot for telecommunication. You know, his idea is either shortly and is for the intercontinental transportation, like airplanes. The second purpose, very beginning, he tried to use this one for the immigration to Mars. Now NASA chooses this one and for the lunar mission, and this is and for the launch vehicle itself this is the purpose. And now when we do the research for the impact to study the impact to the telecommunication and satellite industry, and you have a very good presentation for the I think from the positive side, how to use it, what have things. For the technically, I still have some numbers, and I go to the how many satellites for the constellation deployment, and I think 300 satellites, right? It can deploy. And now you can see that if they use the Falcon Heavy, they can still launch like 50 to 60 satellites. So by the ratio, if you're thinking about the price, unit price per one satellite, how about the price per one satellite? If you use the Starlink, no, not Starlink, use the Starship to launch the Starlink satellite, unit price.
Thank you for your question. Justin will have your answer.
So I actually did some of this research for my individual project. I wish I had the actual number for you right now, but each Starlink satellite costs roughly about $300,000 to manufacture, and the cost for a reusable Starship launch is $10 million, so you can do some math with that. But I know, if I remember exactly correctly, I know to launch 4,225 satellites with Starship, it would cost $1.31 billion, so, yeah.
Yeah, because when we're talking price, we say it's roughly 1/3 of the price, 1/10 of the price, and compared for the, if you use some other kind of launch vehicle. This is the first issue. And the second issue, do you also check about the capacity for the geostationary Earth orbit? If we launch the cargoes to the geostationary orbit, how many tons you can launch to the place? Geostationary orbit?
You mean that like how many tons we can launch to the geo?
Yeah, yes. Because at this moment for telecommunications, we are talking about the low Earth orbit and also the geostationary orbit.
Yeah. So right now, like we only know the actual number for the LEO, that is like 100+ tons. But for the geo, we don't have the actual number. It is not written anywhere in the SpaceX website or even in the Starship booklet. So we don't know the actual number, but the number would be around 25 ton. But there is no actual value.
Okay. So maybe afterwards you can recalculate it. And my recommendation is that for this report, and you should also emphasize something more about the disadvantage if we use this one, because at this moment, and there are so many new space company, and they are developing the small launchers, or there also must be some advantage to use it. Otherwise, why they should get into this kind of business? This is just my personal recommendation.
Thank you for your questions.
Okay, now I give this floor to Walter.
Yeah, thank you. Thank you for the presentation. I also saw something very novel on it, is that you can circulate a number of the members of the team in every scene to present. That was very nice, in fact. It's interesting, the links, I must a little bit agree with Virginia. Sometimes the links between the scenes was, for me, a bit difficult. But as a presentation, very nice, yeah. On your business model, you assume that you're going to change every 5 years big parts of the constellation. Okay, we can discuss about the 5 years, but that's okay. So every 5 years you can launch again a few hundred satellites. But we all know that some things will happen in between. You talked about laser attacks. You didn't talk about, in my opinion, much more important, cyber attacks, and so on. So you may have locally a part of your fleet which is damaged. Let's say 20, 30 satellites are damaged. What are you doing then? Again, launching a big Starship with 400 satellites to repair to replace the 20. So what is your interim solution to replace not big amounts of satellites?
Definitely, I can give this to Justin.
So, as part of our company strategy, we will have we will invest in our cybersecurity team to alleviate threats from cybersecurity attacks. And part of our strategy is actually to launch enough satellites where we have enough redundancy that even in the case if we lost 20 or 30 satellites, we'd still be able to provide coverage with similar quality.
Okay, that's a strategy. By the way, I have to come back to an answer that you gave to my colleague, to Gongling Sun. You estimated it, I take it, but are you able to find enough market to launch 25 times in GEO per year? Do you know how many GEO satellites we launch per year? How are you going to fill your rocket with 15, 20 satellites? That means 500 satellites per year? They are not there.
So if you actually see, then if we have the Starship, so it has the more volume. So as we already discussed, if you have the more fairing volume, then we wouldn't have to go with the very complicated satellite design. Because right now most of the companies are putting more effort towards the very small designs, very complicated design, very complicated integration methods and everything to improve the design. But we have the larger fairing, then we can easily go with the very simple designs. So the development time of the satellite will greatly reduce. As the development time is reducing, the total development cost will reduce. And again, with the Starship, the launch cost is very low compared to other launchers. So if we consider the whole constellation, the total cost will significantly lower.
It's a bit of a problem in your explanation. The launch cost is low if you can fill the whole payload, but if you have to launch 2 satellites, I don't think you can compete against an Ariane 5 against another launcher. No way, because your launch cost is low if you divide it. It's like a serial production, but if you only have, and you will only have a few satellites, you only have 50, 60 satellites per year in GEO. You can only launch 2 or 3, I think your launch cost will be very high. Or am I wrong?
No, I think you're completely right, but I think we need to not forget that Starlink, the real goal actually of Starship, is to go to Mars. So I think actually is one of our conclusion or our discussion is Starship SpaceX is using Starship to launch at some point Starlink in like the first things, like to be able to deploy quite quickly their constellation. They will maybe deploy more satellite when they have the time, but we need to not forget that the ultimate goal is to go to Mars. It's not just like a launcher as Ariane 5, or the goal is to be at the top of the market of the GEO satellites. And Ariane 5 can just do that. But Starship, you have other like men actually driver behind that.
Fully agree, but what you're virtually saying is that using Starship for telecommunications is an excuse to steal rockets.
So, thank you very much, Walter. And also, I think from your presentation, you presented things about how information need for terrestrial application will drive the satellite telecommunication market. So yeah, this could be a kind of projection to how much satellite will be launching in the next few years. Okay, so I'm just going to run through questions from Bonabe Osborne and also Wande Dalma. So from Bonabe, he said, for the type of mega constellation that you are proposing, you highlight that there are some significant environmental impact, visual pollution, manufacturing impact, etc. Is there a need for corporate social responsibility policy to be developed to offset this? Any thoughts on how companies could implement this in practice? Yes, and also, what action can be taken on this? It's actually like 5 questions, so just allow me to read it. Then I will give you my PC, you can just then look through it. I just want everyone to get You have focused on small satellite constellation. What is the engineering challenges in accommodating these many satellites in a single launch vehicle during launch? The clamshell fairing is challenging. Can you expand on the concepts for storing small satellites? Is there a need for additional capability for collision avoidance during initial deployment? The third one, you are proposing a use case that might compete with Starlink. What are your thoughts on the accessibility of Starship for this type of customer? Any parallels from history or current events? Next one, why does Starship have a high impact on small satellite LEO constellation in comparison with GEO large satellites or large satellites in LEO? And the last question from Bonabe, there would be significant resistance to drastic reform to spectrum management by those who currently have spectrum licenses. Do you have any suggestion for how to address this? And just the question from Wande Dalma, we have understood from your presentation that Starship will make access to space more affordable to all nations and companies. What are your recommendations to avoid that the current technology transfer barriers will prevent certain countries from this benefit? For example, ITAR and other regimes that limit the proliferation of dual-use technology. So I will just bring my PC to you and you provide all the answers.
Thank you for your questions. I think we have a taker for the first question, and then we'll move on from there.
Thank you very much. I will try to address that very quickly. In terms of environmental impact in general, that was also a little bit related to my IP. We think that there is a need to increase the dialogue and also the awareness on space situational awareness, promote the share of the best practices and lesson learned within all the space actors, but also set a kind of framework for all the new space actors coming in order to increase the sustainability and better use of space. So just to say, the environmental impact will be huge and increasing, not only in the space industry like the launcher or only in space, but also within the entire supply chain. And therefore, there is a need to consider that to set the standard, like the legal framework, in order to promote best practices for environmental management. And one of the suggestions is to use the integrated space, like integrated management system that's combined the quality requirement, safety need of the space industry, as well as the environmental challenges at the same time. Thank you.
Thank you, Charles. And I believe Swapnil can answer another one of Barnaby's questions, and then we'll go to Wanda Delmar's question as well, and then that'll be our time.
So thank you for the question. So the question is, what is the engineering challenges in accommodation these many satellites in the single launch vehicle during the launch? So it is true, like if we go with this Starship, then we can accommodate like hundreds of satellites at a time. And that is a major challenge, because we need the payload adapters, we need the dispenser to put the satellite into required orbit at a required orbital velocity and all these things. So as during the engineering meeting, during the presentation, as like Laura and Anastasia mentioned, currently Starship is planning to use the same adapters as the Falcon 9 and Falcon Heavy, so that they can get maximum customers from the market, because right now like everything is going towards the standardization. But the problem would be the size, same thing. So if we are changing the satellite design, then again like the accommodating all the things would be a challenge. But Starship, the SpaceX mentioned that like depending on the satellite design, they can design the own dispenser and the own adapters. So I think like if you have the smaller satellite, then again like you can use the Falcon 9 fairing. But if the satellite design is too large for the adapters, then SpaceX can design the like particular adapters. So I think for now it is like in the solution form.
Thank you, Swapnil. And our final question will be answered by Sammy.
So thank you, Random Demo, for your questions. As mentioned by Professor Gonglingson, one of the key focus for Starship in the future is intercontinental travel. So we think that Starship launchpad, Starbase, will be set up in several continents, and then it will allow all nations to join Starship benefits and to launch their satellites using Starship, because we will have a Starship launch base everywhere on the planet.
Thank you, Sammy.
Okay, so thank you very much for your presentation and for the brilliant answers to the question.
Thank you.
So once again, congratulations for excellent performance and good teamwork. So thank you, Taiwo. Thank you, faculty, for your questions. Thank you, Barnaby and Juan, for your questions online. Unfortunately, we don't have any more time for more questions. So now I'm inviting Professor Bertrand Goldman to introduce the next TP, TP Direct Energy.
Good afternoon, everyone. So after this very interesting presentation, we will move on to the second TP. And I'm honored to introduce the team of 16 students, 9 nationalities in our case, dedicated to directed energy mission towards Proxima Centauri B. So as the students organize the stage, it's been a joy for myself and for Professor Hill, my colleague, to lead and to follow this team over the course of the past 6 months when they have worked on this project. And it is a difficult project that they have tackled with compared to the project that we have just looked at. That's very near-term perspective. The project was a very long-term, uncertain project. And I think they really have tackled this question with enthusiasm and lots of interesting ideas. So I'm not sure if you are already ready. Not yet, but all right. So we will have, I think, 7 or 8 students presenting in a more academic setting. But I'm looking forward to it as well.
Hello.
All right, so. All right, so the slides are being set up, and I believe the team will soon be able to start. And I will pass the floor first to Oriol, who will guide through the presentation.
Please bear with us for 2 minutes.
I can confirm that the last time that I saw this presentation, it went very smoothly. So. I'm hearing about interference. So not just in communication, but also around presentations.
Thank you.
Dr. Bertrand Goldman, as well as all the ISU staff whose help and availability has allowed us to achieve what you're going to see today. Secondly, we would like to thank Dr. Pete Warden and James Shalkwick from the Breakthrough Initiative, who actually came up with the topic of this presentation. And thirdly, and most importantly, during this project, we had the opportunity to interact with several experts who are actually developing the things we're going to be talking today. Again. So, now that we know who we are, let's set back and to the beginning of this project. Dr. Pete Warden from Breakthrough Initiative contacted the ISU to make sure that this MSS22 team project would have the topic of direct energy, something they actually work professionally in. We assembled a team and we started November 3rd, 2021. And more than 10,000 hours of accumulated work has culminated into what we call Mission Explore. Explore stands for Exosolar Probe Laser Propelled at Relativistic Speed. This project outlines a mission to the Alpha Centauri system, our neighboring star, as a technological proof of concept, but also as a scientific mission. This mission will use what we call directed energy mission and technology to propel spacecraft to up 20% the speed of light, a journey that will take 20 years, which might sound long, but it's unprecedented. The outline of this presentation is going to be based on the questions we asked ourselves when we started this journey. So we're going to talk about science, technology, even secondary missions. During this presentation, I will be inviting my colleagues from Team NUE to talk about these topics in particular. So let's begin. Again, sorry for this. The main question that we started asking is, what will be the journey? Why are we going there? What is the mysteries to unveil? For that, I'd like to invite my colleague Tushar to give insights on the science behind our mission.
Thank you, Oriol. There are innumerable suns and an infinite numbers of Earth revolve around those suns. Just as the 7 we can observe revolve around the sun, which is close to us. With that, I welcome you all, and I will take you through a journey of science through this mission. My name is Tushar Goyal, and I'm an aerospace engineer from India. Above here, you can see the mission objectives and the science objectives of this mission. All these numbers, all these objectives are not only objectives, they are checkpoints for humanity's mission to become interstellar. We start at Earth for ground and on-orbit operations, and we take a 20+ year journey to Alpha Centauri system. The next main objective is the heliopause and the interstellar medium. Only the Voyager probes have been to the heliopause and the interstellar medium. If we reassign the Voyager probes to go any further to Alpha Centauri, they will take millions of years to reach there. The next important milestone will be the Oort cloud, the boundary of our solar system. The next one will be the astrosphere of the Alpha Centauri system. And the final destination, the Alpha Centauri system, and our target, Proxima b, where we'll reach and look for life. Let me explain these to you in detail and why we choose these objectives and why are they important. First, the interstellar medium. As I mentioned, only 2 probes have been in the interstellar medium. We don't know much about the density and the radiation environment in the interstellar medium. Our probes are going to venture in the interstellar medium to map the density and the radiation environment continuously. This will provide us comprehensive data about the interstellar medium. The next is the Oort cloud. The Oort cloud comes after the interstellar medium. It's in the interstellar medium, and it's the boundary of our solar system. It has millions of icy objects like comets. We have indirect proof that this is a spherical cloud that surrounds the whole solar system, but nobody has ever seen it. For the first time, our probes will get into the Oort cloud, click pictures, and we would see firsthand how the Oort cloud looks like. Going ahead, we'd enter the interstellar medium again and keep on recording density and radiation environment. The next is the Alpha Centauri astrosphere. What is an astrosphere? Astrosphere is similar to the sun's heliosphere, the boundary at which the solar winds end, the extent of the sun's atmosphere. Similarly, other stars have an astrosphere. Nobody knows where this astrosphere begins. We don't know what is the length of it for any other star. But we are going to find out in this mission where the astrosphere for the Alpha Centauri system begins. Why it is going to be different? Because it's a different system. It's a system which has 3 stars, much different than our own solar system. Our solar system has just 1 star. This system has 3 stars, Alpha Centauri A, a G2V star, slightly bigger than our sun. Alpha Centauri B, a K1V star, slightly smaller than our sun. And Proxima Centauri, a M5.5V star, which is very small than our sun. It's a red dwarf star. Why did we choose this target? It is the closest star to us. It's 4.2 light years away, 40 trillion kilometers. These are the most abundant stars in our galaxy. 70% of our galaxy is made of red dwarf stars like Proxima Centauri. They range between masses 0.08 to our sun's mass to 0.4. They are known to be very much more magnetically active. Going to our final destination, and how did we choose it? Proxima B. The Proxima Centauri system, we have detected 3 exoplanets: Proxima B, Proxima C, and Proxima D, which you can see here on the screen. You can see this green zone. This green zone represents the habitability zone of a star. The habitability zone of a star is the distance from a star where a planet can hold liquid water on its surface. Proxima C and Proxima D are outside this habitable zone. Proxima B is right in the beginning of this habitable zone and can be potentially habitable. We know from previous observations from Earth that it's potentially a rocky planet. It's 1.3 times the mass of Earth, approximately, in the habitable zone, may sustain liquid water, and nobody knows it may consist of life. But we don't know that. We're going there to find this out. This is the reason why we chose Proxima B. It's the closest exoplanet to us in the habitable zone. There is not a better target than that. It's right in our cosmic backyard, and we can do more research. A flyby to Proxima B will allow us to study the other 2 exoplanets as well. It will allow us to compare our own solar system with another system. We have never seen another system of planets and stars up close. We would like to compare it with our solar system. We would like to see if that system has an Oort cloud. Does that system have something like an asteroid belt? Do these planets host moons? Are there any other exoplanets present in that system? This mission will allow us to detect all that and study all that. How are we going to do this? For this, we have identified scientific payloads through the course of this project. These payloads, we plan to launch 10,000 probes to the Alpha Centauri system. Why we plan to launch 10,000 probes? Because we think that only a few can make it. That is why we need such a large number of probes. We have identified 4 main payloads which will be present, which will be distributed equally amongst those 10,000. 1 on every 2,500 of those, so that we can gather maximum amount of data. Let's talk about them in detail. The first one, miniature atomic scalar magnetometer. It'll be used to map the magnetic fields and the magnetic environments of the stars and of the planets. The second, electron multiplication technique on CMOS will help us to capture pictures at speeds of 60,000 kilometers per second that our space probe is traveling at. This technique can even detect a single photon and will capture multiple images to produce an image. We'll gather all the photons it can to produce these images. The next one, circular spectropolarimetric sensing. This will be used for detecting homochirality, which is identified as an important biomarker by astrobiologists all around the world. The next most important one is the infrared and the visible sensors. These will be used to detect methane, ozone, and atmospheric parameters that are important for the sustenance of life. There is one more payload, that is the back sampling chain circuit technique, which will be inbuilt into the onboard computer, the heart of this space probe, which is our chip that you can see here. That payload will map the radiation environment all through its journey. It will see what is the radiation environment in our heliosphere, getting out of our heliosphere, going into the interstellar medium, in the Oort cloud, back into the interstellar medium, and going into the astrosphere of another star system. It'll provide us a comprehensive map of radiation environment in our cosmic backyard. All these 4 payloads will help us push the boundaries of science beyond, will help us to accomplish our mission and acquire important data to justify this mission. With that, I would like to pass the floor back to Oriol. Thank you for listening.
Thank you, Tushar. To summarize the science section, we've seen the outline of the journey that we're going to take 21 years from Earth to the Alpha Centauri system. We'll study multiple celestial bodies that will cross, most of them uncharted so far by humanity, and also approach a new solar system. How are we going to do that? By using small sats, a chipset, that will carry scientific payload that will send back to Earth this information to build a better model and understanding of our solar system and our universe. We've seen how and why are we going to do this, but we need to understand better the technology behind this. What is direct energy particularly, and how do we use it? We are talking about accelerating a spacecraft up to 20% the speed of light. How do we do this? For that, I'd like to introduce my colleague Ashish that will give us insights on the technology of this mission.
Thank you, Oriel. I want you all to take a moment and understand the magnitude of our mission. The direct energy mission will take more than 20 years at 20% the speed of light. My name is Ashish. I'm also an aerospace engineer from India, and I am here to tell you how we will accomplish this inspirational mission. So here in this visual representation of our whole mission sequence. So let's start from the ground. At the bottom left corner, you can see our Earth, and on Earth you will see our laser segment, which is a laser propulsion system. The dotted line above the Earth is a GSO. The GSO is geosynchronized Earth orbit. On that orbit, mothership satellite, which we call as a mothership, will be placed, and in mothership there will be 5,000 probes. The probes which are definitely are spacecrafts. The size of these are square in shape, and this spacecraft reaches to Alpha Centauri star system. Now let's look depth into these segments. Again, from the ground. As per the current technology, this mission is close to impossible. For example, imagine if there is a flight from Earth to Alpha Centauri star system, it will take approximately 6.5 million years to reach Alpha Centauri. We aim to utilize a new direct energy method of propulsion using a ground-based laser system, which is situated in Atacama Desert in Chile, to get there faster. We will use a group of 76 free electron lasers, which consumes 5 gigawatts of power each, which sum up to 380 gigawatts, which is equivalent to approximately 50,000 average US residential consumption per day. Our team proposes to use a nuclear power plant to accumulate this rate of power consumption. Our power is generated. The laser operation sequence will commence, as you can see on this pictorial below. So in this pictorial, we see that the white dot represents the ground segment position, which is nothing but our laser arrays. The yellow dot represents the position of Proxima Centauri at each time through a local Chilean time. And remember the main output of this image is the 4 red lines. It represents that we are launching 4 probes per night. Now we have discussed the ground segment. We will analyze the next necessary milestone, which is the satellite. Our satellite that we call the mothership. Mothership will be launched in a neutron rocket manufactured by Rocket Lab in New Zealand. We choose this rocket because our mothership is big and will fit in the volume capability of the rocket. This rocket also has the capability to take a satellite of this size to GSO orbit. Now that we have launched our mothership into GSO, let's go into more details about the satellite, what the satellite will do. So in this schematic diagram, you can see the mothership. At bottom side, you see the thrusters, and there are 4 solar arrays to power the satellite. The main components of this satellite is to launch the probes. So this cylindrical component is a container. There are 2 containers totaling up to containing 5,000 probes. So, and the above there you can see the remote manipulator system, which is nothing but a robotic arm. So the robotic arm takes one of the probes, point towards the Alpha Centauri star system, where it has the capability to correctly determine the Alpha Centauri, where the Alpha Centauri star system will be from 20 years. It points there, it deploys the probes, and then it pushes to a certain point where the laser system can accelerate this probe to 20% the speed of light. Remember the total capacity of this mothership is 5,000 probes. So now our satellite is loaded with the first batch of 5,000. We need to deploy them. Once this 5,000 has been deployed, a resupply mission will be delivered with the next batch of 5,000s. Okay. So looking deeper into the specification of each probe, we can see the square shape of this sail. The sail is giant structure that is 7.5 meters, which is the equivalent of two car lengths. These sails are made of highly reflective materials, thinner than a paper. This makes this sail very light, which a total mass of this sail is approximately 10 grams. This material helps us to achieve the necessary speed which we need, like 20% the speed of light. So let's now look at this tiny chip which is the heart and brain of our mission. This chip has all the components necessary to fulfill the scientific objectives of our mission, all in the size of a credit card. The 4 scientific payloads which was explained by my colleague Tusha will be equally distributed to 10,000 probes. Here in this image you can see the undeployed form of the probe which will be contained in mothership. So the size of this whole system is approximately slightly bigger than your cell phones. Now that we have worked our ways from the ground up, this is the pictorial representation of our mission in a broader context. Here you can see Earth, where the lasers are situated. Here the dotted line represents the GSO, and the point MS here represents the mothership. The point C, which is a contact point. The contact point is the point where once the mothership takes the probe and launch at point. The point C is the point where once the probe reaches to point C, laser fires the probe, and probe accelerates to the 20% the speed of light. To do so, probe and laser has to make contact for at least 12 minutes to accelerate that system to 20% the speed of light. As a summary, this explains us that the probe can reach at certain point, and as okay, thank you, and this concludes the technology section of this presentation, and I will pass the floor to Oriel.
Thank you very much, Ashish. So to summarize the technological part of this mission, in order to propel our spacecraft to Alpha Centauri, we need a mothership to deploy these probes. These probes have to deploy their sail, which is made of reflecting material, be positioned into a specific place, and then fired with ground lasers that we're going to position in the Atacama Desert in Chile. This firing will take around 12 minutes, and we expect that this will propel the spacecraft 20% the speed of light up to their objective. Of course, such ambition and long-term project requires good management and strategy. What are the risks? What are the costs of such missions? For that, I'd like to invite William to give us an insight on the management part of the mission.
Thank you, Oriol. Hi, my name is William Moretti, and I'm a software engineer from Montreal. So let's talk about how to manage this project. So first, we had to decide what kind of organization was best for the first phase of our project. We compared a for-profit against a non-profit, and without going into detail, we chose to go with a non-profit. Here on the table on the left, right, we see a SWOT analysis for the non-profit organization. I'll just highlight the main points. So for the strength, the non-profit benefits the public good, which will help to engage the public and gather support from multiple parties. In terms of weaknesses, non-profits has high administrative overhead, as well as revenues and expenses are strictly monitored. In terms of opportunities, a non-profit can attract large international legacy investors, which will be critical for the funding of this mission. And finally, for the threats, finances are open to public, and any commercial activities will get taxed. Next, we analyze multiple countries to determine where would be best to locate our organization, the headquarters. And so we analyze several factors, such as the ease of doing business, launch capabilities, and manufacturing capabilities. And we ultimately decided to go with New Zealand. The main reason behind it being that international investors are more likely to be attracted and to invest in a non-US organization. Otherwise, the US would have been our first choice. It is important to note that the nonprofit will apply only for the first phase of our project, and our goal would be to attract a major investor, which will ultimately decide to continue with a nonprofit or to switch to a for-profit. Let's now talk about how much it will cost and how to pay for it. So we estimate the whole project to cost around $100 billion. All estimation here are in present USD money. So in the table on the left are the high-level cost breakdown. And as we can see, the highest cost will be the construction of the laser array. So the majority of those costs will span multiple years and won't be required before several years after the start of the project. In terms of funding, we identified 4 kinds of funding that we would seek. First one being crowdfunding, next sponsorship, then legacy funding, and finally the spin-offs, which will generate the majority of our funding. So let's talk a little bit about each of them. So first, the crowdfunding. So to start the organization, we plan on running a crowdfunding campaign with a goal of $500,000 and to offer various rewards. Those rewards will span from a simple thank you to attaching their name to the probes, as well as to tour the laser facility. So to invite people to invest, we created the following video. So while you're opening your wallet, let me tell you about the next type of funding. So next type will be the sponsorship. So we will seek sponsorship from large legacy investors as well as corporations to assist in initial manufacturing and infrastructure costs. The sponsorship approach will be a race where the sponsors will attach their name to the probes and will follow them throughout different milestones through their journey up to Proxima Centauri. And so earlier launch will be, as mentioned in the table, will be auctioned at a higher value since they have a better chance to reach their milestones first. And later launches, such as the STEM sponsorship, will be offered to STEM programs to engage younger generations. Next, we will seek international wealthy individuals that will aspire to attach their name to such a novel project, such as Yuri Miller with Breakthrough Initiatives. And we can see here the distribution of the top 100 billionaires in the world. And so this highlights the importance of being international. Yep. Oh, I forgot to mention, yes, as an incentive, our laser array will be named after our largest donor. Sorry. So last category of funding will be spin-offs. So as we anticipate a lot of research and development, we expect that major technological breakthrough will be done throughout the development. And we rely on spin-offs funding, which we identified major spin-offs here. For example, the highly reflective sail material, which could be used for solar reflector or passive cooling application, etc. Then we have the graphene manufacturing, which has already been identified as a major disruptor in many industries. Next, we have high-density energy storage to help with the renewable energies and to fight climate change, as well as the next generation batteries. And finally, the miniaturized camera and sensors for medicine and surveillance camera, for example, applications. And finally, such a large project has its risk. So we highlighted here the major risks. One is the mothership failure, which could be mitigated with extensive tests as well as system redundancy. Next, we have a timeline shift, which will be mitigated by transparent processes and accountability. Next, failure to find large legacy investors, which will be mitigated through having a good management and marketing team. Then the failure to generate profit from spin-offs, which will be mitigated by having, throughout development, having IP recognition, intellectual property recognition. And then finally, the rejection from Chile to allow the building of the laser array, which would be mitigated by establishing good relationship early on and offering operational and educational incentives. So as a summary, it is a high cost, high risk endeavor, but it is feasible, especially with a good management team and as well as good risk management. And with that, I will leave the floor to Oriol.
Thank you, William. To summarize the management section, Team NUE suggests a non-profit organization based in New Zealand and estimates the whole cost of the mission to around $100 billion current estimates. Most of this cost is attributed to the technology to be used. And in order to pay for it, we're looking for different ways of funding. One of them, the crowdfunding video have you seen, but also legacy funding and spin-off technology. We've talked about ambitious tech, ambitious science, and management objectives. To what extent do they clash or can be enabled by policy and law? For that, I'd like to invite my colleague, Valentin, and to give us the policy and law perspective of our mission.
Thank you very much, Oriol. Hello, everyone. I'm Valentine Laurent. I'm from France, and I have a master's degree in architecture from the National School of Architecture of Versailles. So, space law. space law can be described as the body of law governing space-related activities. Much like general international law, it comprises a variety of international agreements, treaty, convention, and United Nations General Assembly resolution. The term space law is derived from the 5 international treaties here on the slide. These 5 treaties deal with issues such as the non-appropriation of outer space, arms control, the freedom of exploration, and many more. The space law is also relative to the 5 set of principles here on the slide too. They are called soft law because they serve as a method of adopting code of conduct. Indeed, treaties can be viewed as too restrictive and not representative of all nation interest in space. In addition of these international instruments, many states have national legislation governing space-related activities. After analyzing of this different legislation and their restriction, we can conclude one thing. No law, national or international, restricted the interstellar travel. Then, one of our principal considerations of law and policy at the national and international would be for the site of establishment of a laser station. Our project includes the use of a laser technology for a large laser array in a desert. It will shoot a beam in the infrared spectrum up to GSO to power a swarm of small spacecraft to another solar system. That's huge. We must think about a safety way to build, use, and operate these devices. As laser is by nature a dual-use technology, it falls under export control regulation. Thus, they would have to be manufactured on-site or would have to be made to import this technology. So we choose Chile. Chile is a country of the southern hemisphere and has no specific law restricting the use of laser, answering some of the mandatory we need for the succeed of our mission. The Chilean government would also like to establish more scientific and technological ties with space farming nation. Moreover, the United States has invested more than $1 billion in astronomy facilities in Chile and recently launched a public-private diplomacy initiative with this country. However, now the question remains if the laser array, the way it is designed today, can be placed in Chile. And if so, what type of regulatory or safety framework are needed to be adapted? Due to misperception of laser in entertainment, such as book, movie, or TV shows, there is a mystified threat about the weaponization of laser. Of course, the operation of a laser requires safety precaution. Laser can damage the vision of pilot and passenger by a direct hit on an aircraft passing overhead or arming satellite flying over. Laser can also be dangerous for the people operating them from the ground. Some solution can be found to mitigate those, but we don't know yet the effect of the operation of a laser can have on the environment. Indeed, Chile has one of the most progressive environmental protection laws in the world and have made significant development over the last few years in environmental action. We can propose a no-fly zone and a safety zone around the laser array to protect flora and fauna as well as humans from potential harm from laser operation. But we can be sure that we will have to do more studies about the effect of on the environment of this kind of new devices and its unprecedented use. Now we have talked about the site of establishment of a laser ground station. We need to determine the best site to establish our business and our communication center. Therefore, we could affirm that New Zealand is a suitable location for space business, particularly that one that involves space technologies. In a little under 2 years, New Zealand has gone from having no national space law to having a new act to regulate space activities. In addition, concerning increased commercial space opportunities, with the establishment of Rocket Lab, New Zealand entered in a treaty-level technology safeguard agreement with the US government in 2016. Moreover, in 2017, Outer Space and High Altitude Activities Act has proposed to include 2 legislation that are quite interesting for the business of our missions. The first one is a licensing regime for space launches, launch facilities, and payloads. And the second one is a legal framework to regulate high-altitude activities originating from New Zealand. That can help us with the operation of our mothership, but also to obtaining licenses for our 10,000 spacecrafts. But under the law, there are two concepts in our mission that we must to look at carefully. The first one is the communication and monitoring of our 10,000 spacecrafts. It is not a problem to obtain licenses, but it can become complex when it's come to monitor them through the 20+ years of their missions. To this project, the preference will be to use an autonomous spacecraft that can be integrated successfully into a swarm. There are no specific limitations on the use of autonomous spacecraft at this time, but maybe policy and legal framework will arise, and we need to be careful about this. The second concept is the way we powered our probe. We use a RTG, that is a thermoelectric generator, which its source is a result of a natural radioactivity decay. To which the framework refer to the NPS. It considers a safe use of nuclear power through the launch, operation, and end-of-life phases, considering the hazardous nature of radioactivity materials and their potential for harm not only people, but also the terrestrial and non-terrestrial environment. Now we are talking about non-terrestrial environment, we need to address the issue relating to protecting the Earth's resources and the resources from other celestial bodies. COSPAR is maintaining the principle that planetary protection policies should enable the exploration and use of the solar system, not prohibit it. That's why they create the Panel of Planetary Protection to develop the policy of planetary protection in 2021. They have the mission to give a clear framework to the planetary protecting. And their main concern is the possible effect of contamination of other planets by Earth material, but also the contamination of Earth by material returning from outer space. For our mission, the likelihood of one or more of the spacecraft alighting on another planet remain unlikely. However, the potential for possible planetary contact during this mission or for future secondary mission could potentially affect planets, even if in our own solar system. I would conclude that current space law dates from the mid-20th century. The space landscape looked vastly different than it does today. Space law must move forward and answer the thought question that continue to arise as a novel issue emerge, such as our mission. Thank you, and I will pass back to Oriol.
Thank you very much, Valentine. So to summarize the policy and law section, Team NUE has not found any major law restricting interstellar travel, but we still recommend looking further into specific topics. The interaction between countries, for example, Chile and New Zealand. Also, the dual-use technology due to the science payload that we're bringing and the technology used to propel the spacecraft, as well as the use of artificial intelligence to enable autonomy. Last but not least, planetary protection is in our mind as we'll scatter multiple probes through the universe. Of course, as this is a long mission, attention to the public is key. For that, I'd like to invite my colleague Chris to talk about the outreach and education strategies that we've come with.
Thank you, Oriol. So I'm going to be introducing the education and outreach section to y'all. My name's Chris Richardson, and I'm from Richmond, Virginia in the United States, and I have a background in international relations and human-centered design. And we're going to start off with our outreach story. So for this mission, we have designed a story called Lux Nada, and Lux Nada serves the purpose of being a multi-platform story that can be multi-generational to help inspire the next generation to want to be a part of this mission and see this mission through to fruition. I'm sure each and every one of you at some point read some science fiction, watched some science fiction when you were kids, and you were inspired by what you saw. The goal here is to use Lux Nada to really drive home the points of directed energy as a peaceful use, and to also show off the multiple applications for directed energy and its associated spin-off technologies to help better the entirety of humankind. So we're going to use this story to really inspire all these people to want to move forward with this mission and to see this future and bring it into fruition. And we do that by setting this story in 2687 far into the future, where we've utilized the research that was done for this mission to build this new world, to build this more energy efficient world off of multiple of the needed spin-off technologies in the energy sector to enable this mission to happen just from the laser firing perspective, and to enable this to happen from the laser firing perspective. And this narrative is going to is about the drive for human exploration, and at its core is presenting the balance of meeting human needs with the urge to explore the beyond and discover the deeper meaning of the universe. So how do we represent humanity on such an ambitious mission where we're sending all these probes deep into interstellar space? We do that through the use of 2 message plaques. The first message plaque on Einstein's payload here on the globe is going to have the names of all of the people that are part of the mission to initially fund this, and it will have the names of all the legacy funders. And we want to acknowledge their accomplishments in being a part of us with this mission and their contributions to it. And then this second message plaque here is modeled off of some of the other message plaques that have been proposed over the past couple of decades and centuries, past couple of decades. And it's a model of where one of the ones that could go on this, but ultimately Explorer is going to need to bring together an interdisciplinary and intercultural team of experts to really design and construct a message plaque that represents all of humanity. To date, most of the interstellar message plaques that have gone into space on other probes have not properly represented everyone on Earth, and we're going to see that that is different on this mission. And by doing that, it will provide an opportunity for us to pause and reflect on our significance in the universe against the expansive backdrop of where we are in interstellar space. Lastly, we want to also help build an ecosystem around directed energy technologies and the associated spin-offs. By doing this, we are going to help build an economy to where these spin-offs can be used, sold, and made to help fund this mission, while also training and getting a workforce and a group of entrepreneurs that are well-versed on directed energy and its potential spin-offs. And we're going to do that through what we're going to call the Interstellar Talent Center, or INTACT. And INTACT is going to be informed by the best experts, scientists, and professionals in the directed energy mission in the developing economy to help inform the students' training and what's going on, so they're following the best practices and moving forward how they can. And with that, I want to thank you and return this to Oriol.
Thank you very much, Chris. So to summarize the outreach and education section, Team Newer recommends the use of 3 strategies to keep the public engaged. First, the fictional use of Lux Nauta's story to inspire and maintain the fire in the imagination of people. Secondly, we want to show and broadcast to the interstellar space and the universe what human beings are. For that, we want to make use of plaques that will be on our spacecraft. And third, but not least, the creation of an institute of talent to both foster educational and professionals that will only not enable this mission, but they will also enable all the economy surrounding the mission. While Mission Explore is happening, this technology used for it will enable and open a world of possibilities. We would like to look at the possible secondary missions that the main mission will enable. I'd like to introduce my colleague Victoria that will talk about the possibility and the secondary missions from our main mission.
Thank you, Oyo, for the introduction. My name is Victoria Arias Rendon. I'm from the United States, and my background is in biology. A successful mission utilizing directed energy can afford many opportunities for extended missions and secondary missions. For example, Voyager's original mission was sent to study the outer reaches of our solar system, but now has passed the heliopause and is studying the interstellar medium. or how New Horizons was originally sent to study Pluto, is now in the Edgeworth Kuiper Belt studying Kuiper Belt objects such as MU69. For this project, we define secondary missions as missions that run in tandem or in sequence to our original directed energy mission. We understand that secondary missions are quite far away from our directed energy mission, but we felt that we wouldn't do the project justice without mentioning them. One of the first uses of directed energy, we can use it for rapid transit within our own solar system. Our solar system is there's still many things in our solar system that are left undiscovered. With current technologies, it can take quite a while for our spacecraft to reach the solar system in certain areas. For example, it took New Horizons at least a decade to reach Pluto, and Cassini around 7 years to reach Saturn. We also understand that in the business, time is money. And long-duration missions can be a financial burden, can also cause commercial inaccessibility. But with directed energy technologies, we can drastically shorten these missions and also open the sector for commercial actors. Other interests of the solar system would be, for example, Enceladus. Enceladus is a Saturn satellite. And Enceladus is very unique because it has an atmosphere, despite having low gravity. Aside from its atmosphere, Enceladus has enormous geysers that erupt liquid. And what's also found interesting with the geysers is that they found organic molecules. The combination of liquid and organic molecules is an interest to many scientists. We also understand for this project that in order to utilize directed energy repeatedly and for secondary missions, we would have to solve the problem of deceleration. Now, there's been quite a few concepts of deceleration that have been proposed. One of them was by renowned physicist, Dr. Robert Forward, and the image you see above me is one of his designs. Once again, I emphasize that this is hypothetical and in no way has been proven to any extent. The use of directed energy can also be used for solar observations. Solar observations can prove to be very useful, especially in the event of another Carrington event. The problem with solar observation with current technology is that to put a spacecraft into a polar orbit would require immense fuel due to the high inclination. But using directed energy technology, we can launch a spacecraft into solar polar orbit, yielding valuable data. Another use for our technology would be for microlensing. When a celestial body has a gravitational field that can bend light, scientists can use this to their advantage as a telescope. By sending a spacecraft to the Oort Oort cloud around 80 billion kilometers away from our sun, we can use our sun to observe other celestial bodies such as exoplanets and perhaps maybe image them, their atmosphere or their surface. As technology improves, we hope to one day use this technology for smaller powered spacecraft. Instead of sending a spacecraft, for example, to Mars, which will take 7 months, perhaps with directed energy technology, we can shorten that time to around 45 days. Another example would be perhaps using the laser for space debris mitigation. But to use a laser for space debris mitigation would require extreme international policy and tremendous global oversight. Other missions using directed energy technologies could be to other interstellar systems, such as the Alpha Centauri system. The Alpha Centauri has 3 gravitationally bound stars and has multiple possible habitable zones. A habitable zone is where a planet is not too far, but not too close to a star, and it's able to sustain liquid water. And as technology progresses, we hope to one day include biological experiments, starting with tardigrades. Tardigrades are small invertebrates. They are 8-legged creatures, and they have been known to survive the vacuum of space, especially radiation and the microgravity environment. They will be the ideal exosolar travelers. And perhaps they can lead the way for future biological missions that can ultimately lead us to human interstellar travel. Much how Felicity and Laika were one of the first animals in space before Yuri Gagarin made his iconic flight. And lastly, we hope that directed energy could be a way to mitigate chemical propellants. Chemical propellants can be a hazard to the environment, but perhaps one day directed energy can be used to mitigate that. The use of directed energy leads tremendous possibilities for new missions and new discoveries and bring us into a new era of information. Thank you, and I will pass you back to Oriol.
Thank you very much. To summarize this section, we've seen possible technology enable thanks to our main mission. We've looked at fast travel inside our solar system, Earth protection, stopping on reliance on our propulsion methods, but most importantly, and our future missions to push biological creatures and maybe humans to interstellar space. In order to conclude and summarize all the things we've seen here today, I'd like to introduce my colleague Ina to talk about the recommendations and conclusions for this mission.
Thank you, Oriol. So, my name is Aina Doyle. I'm from Ireland. I have a background in astrophysics. As you've seen over the course of this presentation, there are significant technical, engineering, managerial, social, and legal challenges presented by a mission of such unprecedented nature. Although the hurdles may seem great, we do not shy away from this. If we are to advance as a species and push beyond our current limits of exploration, we must embrace these challenges. In the words of John F. Kennedy, we choose to do these things, not because they are easy, but because they are hard. As a team, we have spent several months up with late nights researching, days spent discussing, putting our heads together, filling whiteboards with calculations, and having deep conversations with external experts to put together this list of recommendations that will provide a roadmap to Alpha Centauri and make interstellar travel with direct energy a reality. So, the first recommendation, to raise the technology readiness levels of the subsystem components of the spacecraft with a very large effort of research, and also to develop manufacturing methods of the advanced light sail material that's extremely lightweight and strong, such as graphene. The second, to also fund research into developing the payload instruments and miniaturizing them and integrating them onto the payload subsystem. This is so we can collect the maximum amount of high-value scientific data over the duration of the mission timeline as we go places we've never been before as a species. Number 3, to secure the laser network from any external influence and to ensure there's no harm to the surrounding environment. Also, to mitigate environmental impact, make more research into developing high-capacity energy storage solutions and also finding sources of renewable energy for the project. Number 4, to establish an international academia consortium to publicize and educate about this mission and to attract investors and sponsors that are going to enable this to happen. Number 5, to expand the competencies of UNUSA or develop an international space union to address the emerging issues relevant to this mission, such as using nuclear energy devices on space missions, and to also look at planetary protection policies. And the final one, to create social impact and engagement with intellectual property such as Lux Nada that are going to inspire a future enabled by direct energy technology and more deep space exploration. And also by developing interstellar talent institutes like Intact that are going to create a new generation of human capital that are going to enable the direct energy economy. And also to include an interstellar message plaque that's going to be representative of all humanity as the first bastion to other stars on this monumental journey. So, with that, although interstellar travel may seem like science fiction, it is possible with direct energy technology. Pushing the very limits of space exploration and getting to speeds at 20% the speed of light, that's no easy feat. But we can rise to this. Our team firmly believes that humanity's future can be written in the stars. We just need to rise together collectively as a species, as a planet, as a space-faring civilization to make it happen. This project addresses humanity's dream of venturing far across the vastness of space to reach other stars, not just from the scientific and technological perspective, but by looking at the pertinent terrestrial considerations from an interdisciplinary approach. In this way, we provide an all-encompassing vision of how we're going to achieve this. Through presenting the Explorer mission to you today, we hope to impart with you a spirit of hope, a spirit of exploration, a spirit of unrelenting ambition to go further beyond Earth than ever before. It is this spirit that continues to drive our exploration of the cosmos and will inspire us to achieve this next milestone in our human destiny. And with that, I would like to pass the floor back to Oriol and wrap up this presentation.
Thank you very much, Ina. This concludes our presentation today. I would like to first thank the audience for being here today, but also the presenters and all our team, which you will recognize by the t-shirts we're wearing. So from now on, we're open for questions. Thank you for your attention.
Thank you very much, Team Directed Energy Mission, for an information-loaded and engaging presentation. I think I will start with the left this time. Okay, that will be your left.
Me again? I'm very clever that way. So you highlighted two countries in your presentation, Chile and New Zealand. It looks to me as if the operations in Chile bear a high amount of risk, and yet having the headquarters of the operation in New Zealand would perhaps be extremely beneficial in a financial sense. Is this fair? Is this right? How would you address a complaint like this?
Thank you for your question. I'd like to refer that to our management team.
Yes, so on the financial side, we analyzed multiple countries. We show them on the slide, which includes more than just New Zealand and Chile. So New Zealand has been selected because there's some partnership with the US, and the US has a large space industry. Yes, so for Chile, no.
You don't need to show me the data again? Really? That's okay.
Put it that way. Thank you. So, I'm sorry, I forgot the question about Chile.
What if someone in Chile says, oh, this is very dangerous, what you want to put it in our country?
Yes.
And yet you're going to make all that money over in New Zealand.
I will.
Apparently, Rebecca would like to answer.
I will pass the question to Rebecca.
Can everyone hear me through this microphone? Okay. So we did do a lot of analysis between Chile. We also looked at putting the laser in New Zealand specifically, although the location for Chile was a lot more beneficial, as well as we had planned on offering Chile incentives through educational programs and additional funding through our organization to make sure that they would be on board. We plan to speak with them early in the process as well to make sure that they are comfortable with everything and we are addressing their environmental concerns. But we did look at other locations as well that would be suitable.
Thank you. Really good job with the storytelling in this presentation. It was very strong and clear and compelling.
Thank you for that question.
Okay, thank you. Very nice presentation. Well balanced content for the different disciplinaries. And for me, I have always the same technical questions. Could you please go to page 15, please? One page, 14 maybe, sorry. Yes. And so for this one is of course the engineering, system engineering is very important. And from here, I can see that the acceleration uses the laser for the acceleration. And for the system engineering point of view, for the satellite, and especially for the long journey, this is extremely long journey, and then we need the navigation. So you should thinking, what do you thinking about for the navigation issues? You use something like a star tracker, because otherwise, you know, if you just throw it there, keep it moving, but for sure you will lose your target. What's your consideration in this part?
Thank you for that question, and I'd like to refer that to Tushar.
Thank you, sir, for the question. So for this, we indeed use star trackers. One important consideration here was that Alpha Centauri system will be moving apparently as well in our sky. Every year, Alpha Centauri system shifts by 3.6 arc seconds. Because of that, we need to and we are taking a journey of 20 years. So we need to estimate where the Alpha Centauri system will be 20 years later. And as we are seeing it in 4 years in past, we need to calculate where it is 25 years later. Our mothership is constantly doing those calculations to deploy the probes at the right location so that it reaches the right location. For every probe, the calculation will change slightly. So there is not a uniform number for every probe. There is the calculation changes with every probe as the date and time progresses. So we have special onboard computers for doing these calculations with the help of star trackers.
Yeah, yes, this is the same. And I mean, for the control, you need the closed loop control system. Otherwise, you will lose the target. This is the first question. The second one is about, I see that from the next slide, you mentioned about that the acceleration period is roughly 12 minutes. And did you also calculate about the acceleration itself, how many Gs it can reach?
How many?
How many G?
How many
like
Gs?
that, yes. Because, you know, 12 minutes is starting almost from zero, because it's compared to 20% of the light speed, it's the orbital speed is nothing. So it's starting from zero to the 20% of the light speed, and how about the acceleration?
So the acceleration, the total time 12 minutes is taken to accelerate to 20% speed of light. So it is accelerating slowly, as we see, but it is not going to get in contact with, we did not put in a gravity constant in this, because the speed is much higher than anything that can capture this probe. Nothing in its path or while it's being deployed can capture this probe due to its high velocity. So no planet or no star could actually capture in its gravity in orbit. So we did not put a G component to it. We calculated the straight up velocity and the time that will require for the laser to fire at the probe to get to this speed. This was dependent on the photon pressure of the laser, how many photons were coming onto the sail, and dependent on the size of the laser sail, which is 7.5 meters in diameter, and the mass of the laser sail as well, which was 10 grams. On the basis of this, there is a paper that has been published with breakthrough experts which gave us the right parameters of 12 minutes, and we did not go with G's. We went with the mass of the sail, the diameter of the sail, and the time it will require, and the energy required by the lasers, which is mentioned 380 gigawatts, is required to propel it to 20% the speed of light.
Yeah, for this one, I also make a very quick calculation. And for this, again, one is for the thermal control. You know, this is very dense the energy. Maybe the first is burn your hardware first, and then everything's disappeared in space already. Second one is if you take the average acceleration, it will reach roughly 10,000 G, and with this period, and then you can reach the speed from 0 to 20% of the light speed. And this is something like the trade-off study, and this is just maybe for your consideration for your presentation in ISC conference.
Definitely, that'd be really helpful. Thank you.
Thank you very much for this brilliant presentation. I think you have done a very brilliant job, and your slides the outlines are very clear and beautiful, and I enjoyed the presentation. So I will start to say that I believe everyone in this room, we understand that space is hard. So the environment, the technology, cost and methodology. And I see that in your presentation, you try to explain all of this. And all of these points lead us to risk. But unfortunately, you never touch. There is no risk analysis or how you perceive risk with this mission. But it's a risky mission. And the chance of achieving this mission, because if the technology is wrong, everything is wrong. You can get some funding, the funding will stop, right? The outreach, people will not take you seriously. You know, all other things will have impact. So how do you perceive risk with this kind of mission? And because to talk about risk, you need to do some kind of alternative mission concept and all this kind of thing. So I just want you to, you know, educate us about your idea with risk. And for your secondary mission, all the secondary missions are amazing, but also all your points are could be, because your secondary mission must be tied in terms of mission concept, in terms of, you know, everything to the primary mission. But it seems that you just, we go to Enceladus, we do this, we do this. If they are not tied, if there is no connection, it will not work. So yeah, just educate us. What do you think about risk, and what is the chance of this mission?
So thank you for that question. To answer it, I will refer to my colleague Rebecca to talk about the risk question. And afterwards, I will pass it to the secondary mission team to answer the secondary mission question. Yes.
Can you go to the slide? Sure. Keep going. Thank you for your question, Professor. I'm definitely going to help you with that. Okay, so we do have a bit of a risk analysis in our presentation, and I know that William did touch upon them a little bit. However, your comment regarding the could be of future secondary missions, a lot of our project is based on assumptions that this material will be accessible, the propulsion technology works, everything that we have put together, well, not everything, but a lot of it is not proven technology. So we don't want to say you can or you will, because we don't know. We hope and we aim to complete that, but as for a definite answer for our secondary, I don't think we're comfortable saying a definitive answer. And also our report has a much more in-depth risk analysis as well, and we do have a QR code for you at the end so you can have access to that. But these are the major risks that we identified up front.
So I want to congratulate the team. You know, you've come a long way. You are not yet, you know, in Proxima B, but you are at least, you know, you've made a long way since you started with the project, and I think it's good. So congratulations on the team for the presentation. Very interesting. You work well as a team. But I wanted to echo some of the points that Taiwo just made. Not on the risk, but because risk is the threat times the likelihood of occurrence. And I will focus on the last part. Because you talk about an ambitious mission that is, or you said you can make it a reality. And all of that seems to be possible. Also some of the concluding remarks you said. So now, if we fast forward to 35 years, what's your gut feeling? Did it happen or not?
Thank you for that question. I think I can answer. First of all, we can provide not evidence, but like as I said at the acknowledgement section, we've had the privilege to interact with actual people who are working on this. And there was one instance in December we actually could participate in one of the breakthrough initiative kind of overall summary of what they've done for their research. And we actually found compelling evidence that this is a thing that is evolving and it's happening, from very thin materials that resist high Gs, from, for example, communications, optical communications, for example, are being developed for different missions. So I don't know. I think if investment, as we've talked in the management section, is provided, and the people make the sacrifice enough to enable this research to happen, I would think that it is possible. Because there's not only the interest for providing it for an interstellar mission, but as we've talked in the spin-off section, there's a lot of technology that will come from that. So for example, graphene will enable like fast battery charging, which is everyone has some battery in their pocket right now. So in that sense, there's not only initiative for the interstellar mission, but there's other factors that will most likely make it happen in the future.
So yes or no?
Yes. 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 Come on, team. Yes. Yes. Hey.
Okay, also from my side, a completely different presentation as the previous one, but systematic. So this has an advantage, maybe less spectacular, but very systematic and very well done. And yes, nice slide. I'm obliged to talk about another risk, financial. You make a sort of business plan, and you expect a lot of income via the spin-offs. So I assume you were hoping on a lot of royalties. You have to sell a lot to get that money. That's already one thing that as a financer I would say, if they have to go for 60 billion or what is it via royalties, that's a lot. Calculate your turnover. But you present a business plan with profit. Now, are you going to do your crowdfunding via equity crowdfunding? Because you make profit.
Thank you for that question. I might refer that to Rebecca.
Thank you. Well, we are a nonprofit organization as well to begin with, and the crowdfunding campaign would not be any type of equity crowdfunding. No, that wasn't the plan.
I wonder if you have such a profit, if the people will give you money for you to make profit afterwards. I think you may have to think about on crowdfunding, on equity crowdfunding, and give them mini shares. The second thing made me very curious. Nothing to do with finances now, but that made me very curious. So, besides giving the Chilean people a night show at 11 o'clock, why are you firing your laser between 11 and 1? What is the rationale for that?
Thank you for that question. I might refer it to my colleague Tushar.
So that depends on the position of the Alpha Centauri at the time when we are in the Chilean sky. So the reason why we put our laser array in Chile is because of the position of Proxima Centauri. It's visible from the southern hemisphere, not very much from the northern hemisphere. Secondly, there are other factors. This has firing it at 11 and 1 is actually scientifically a little less efficient, and firing it at times when Proxima Centauri is in top of our sky would be more efficient because we have to go through less atmosphere. But we had other considerations like flight paths, which we checked, and there were other considerations like when we don't want to disrupt terrestrial organizations. So we tried to take in as many terrestrial considerations as well as the position of the stars.
Okay, I expected the flight patterns to be one of your that you don't make holes in different planes. Thank you very much. I think we're going to close it now. So I hand over back to you.
Yeah, thank you, Professor Hill.
Thank you so much, Bertrand. Great work, guys. Many congratulations. Just a couple of questions, if I may. One is very nerdy, I have to say. Have you thought about the probability of collisions between your probes and Oort cloud comets?
Thank you for that question. I might refer it to my colleague Tushar.
Yes, sir. That is the reason why we have selected 10,000 probes, because that is one of the reasons that some of the probes won't make it. The current density, we know some of them would make it, but we do expect collisions of some probes in the Oort cloud with the comets. that's why the decision of launching so many probes was taken.
Yeah, but the question was the probability. Have you given any consideration to statistical models?
For models, we look into some models. There are some models that suggest there are millions of objects. Some models suggest there are less number of objects. Some models suggest that the Oort cloud extends from 2,000 to 200,000 AU. Some suggest 1,000 AU to 100,000 AU. There is not an exact number of objects available. So we did not make a statistical analysis because we didn't have any consistent numbers on how many objects or what is the density of the Oort
Okay,
cloud.
so the variables are not so well established.
Yes.
Okay. Do I have time for another question? Yeah, thank you. And this is kind of a follow-up type of question. Likewise, do you anticipate significant problems associated with cosmic rays?
Again, thank you for that question. Tushar will continue answering.
So we do estimate some problem with cosmic rays. Traveling at 20% the speed of light, even an atom can be harmful for the sail. Even an atom could be at such high energy that it might rupture the sail. And we do have made calculations. That is why we are also mapping the interstellar medium and the density and the particles in the interstellar medium, because that is also currently unknown. So we don't know the exact numbers. We have seen that there can be a model generated on the basis of the electron gun experiment, when we can put something in the front of the gun and see how many electrons would actually pass through the material that we put in. So depending on that we can, but the density of the interstellar medium is unknown, and how we will be in the galactic how we'll react with the galactic cosmic rays is unknown. That is the whole reason for 10,000.
Yeah, and remember that some cosmic rays have, believe it or not, velocities are close to 99% of the speed of light itself in the vacuum. One final question, very quick. This question will probably shock Professor Peters. He says nothing shocks me. Yeah, well, the question is this, and it might even shock Professor. Just to clarify something, is anybody in the world currently wealthy enough to fund this project?
Good question. I'd like to pass the microphone to answer that question to William.
Yes. So there's up to 2,750 billionaires in the world and more than 20 million millionaires, which makes a lot of the bulk of what we would seek. So a single investor wouldn't be enough, I think, because they would probably have to watch their whole fortune go away. But that's why we're seeking to find multiple large legacy investors internationally. But our main idea would be to target one main, so we can name the laser array after him or her.
But could, for example, Elon Musk fund this project?
So we thought of it. However, he's already invested in space endeavors, as Richard Benson, as Jeff Bezos. And so we think that they wouldn't touch our project because they're already invested in their personal space projects. But such a novel such a novel project could maybe arise or rise their interest. So it's unknown. We would have to ask them.
Okay, many thanks, and again, very well done.
Yeah, thanks a lot for the presentation, and again for all the months that we kind of spent together with you on this project. Yeah, I will give Tushar a break, and maybe my colleagues have asked about risks, and whether the project will happen in 35 years, maybe 300 years, maybe never. That's one thing. But the communication and the outreach that you are planning right now, that can take place and have some level of success. I would like to comment on this, maybe also mention the podcast, please.
Thank you for that question. I'd like to pass it to the Risto. Please.
So yes, the communications of this project could stand in a vacuum on their own. They would talk about a lot of things as they're written right now. They would help inspire us to still look towards the future. So maybe it could go towards other interstellar probe projects that would come after it. But we specifically do want to start a discussion around the peaceful uses of directed energy. As we've probably all seen and know, directed energy as we talk about right now, is usually talked about in a defensive and offensive weaponry capacity. And we want to help shift some of that focus on the current ideologies around it to the peaceful uses of it and how it can be used to further and better humanity as a whole. As you mentioned, there's some additional communication stuff that we're worked on. We do have a podcast that you can find at this link. You can also find our poster, our exec sum, and our final report. And you should also be able to find links to some of our social media that we established just for this organization as itself. But the mission's own communication strategy, not the external public relations strategy that I just mentioned, is designed in a way where it can still provide this inspirational future, but maybe it wouldn't be for this mission depending on how things played out, but it could still be there.
All right, excellent. And we have one question from Juan Del Mao, who is asking, as you know, telescopes, both Earth and space-based, hello Juan, allows us to see things we have never seen before. Have you looked at possible evolution of astronomy during the 20-year missions and how they could impact your own science objectives, i.e. make them obsolete? In other words, have you classified your science objectives in order of priority? I guess that's back to you.
Thank you for that great question. I would like to pass it to Tushar.
Thank you, sir, for that question. That's a great question, and that was a huge consideration while we were doing this project, that we have to identify these science objectives, that if in 10 to 15 years there are leaps in astronomy, our science objectives cannot be held back. So we identified those objectives in that manner. First one, I would say, is taking the picture of the planet would be vital for this mission. That would be the topmost mission priority. Secondly, probing the interstellar medium and the radiation environment, going from one heliosphere of the star to interstellar medium to another astrosphere is important, and I don't think we'll be able to do that from any telescopes. So from the telescopes that are coming in the future, like the James Webb Telescope and the Extremely Large Telescope, we identified what those telescopes might not able to do, and those were the objectives that we identified for this mission, which was really important, because we don't want our mission to be obsolete coming in 20 years, because this is a future mission.
All right, well, I think with this, we close this presentation of UTP, and I pass back the floor to Daniela.
Thank you, Bertrand. Thank you. We would like to thank all MSS22 students which they involve their efforts for both TPs. So thank you to all ISU staff, faculty, also external advisors, sponsors, and we wish that this type of collaboration between our students continue after this TP, and we wish them great success on next conference coming IAC in September in Paris. So all the best to all of you. I will pass the microphone to Nicola to close this program.
Thank you, Daniela. So for the audience in the room, for the audience online, you know, it's important to recall that it was this presentation, this TP presentation is an important milestone for our students. Not only because it culminates 6 months of work in different constellation in terms of teams, but allow them to produce a report of excellent quality. But now they are also embarking as of tomorrow in a new journey, because this brings these activities to an end for their journey at ISU, and they embark now into the internship. So for the audience online, I think it's also important that you realize how important it is for this class. It's because it's the last activity that we'll do as a team in the context of ISU. So that's also is very important, and I'm sure that tonight they're gonna celebrate. Not only because they're happy it's over, because they're gonna celebrate, because they deserve to celebrate. So thank you very much, and I will say good night, good evening, and good morning wherever you are online. So thank you very much.